Hello there, and welcome to Nightfall Science. Tonight, we travel gently beyond Earth, discovering why space feels stranger, quieter, and more uncertain with every kilometer. Let your shoulders soften. Let the distant stars remain still. Let's begin. Space does not begin with a sudden edge. There is no solid border where the sky ends and the universe begins. Earth's atmosphere simply becomes thinner with altitude. Air molecules grow farther apart. The familiar blue gradually darkens. Eventually, the space between particles becomes so wide that ordinary flight is no longer possible. A conventional boundary, called the Kármán line, lies 100 kilometers above sea level. It is often used to mark the beginning of space. But even above this line, faint traces of Earth's atmosphere continue much farther. Individual particles still surround satellites. They are extremely sparse, yet they can create a small amount of drag. This is why low-orbiting spacecraft do not remain at the same altitude forever. They slowly lose energy. Their paths descend unless engines raise them again. The International Space Station travels roughly 400 kilometers above Earth. From the ground, this sounds very far away. Yet compared with the size of the planet, it remains remarkably close. If Earth were represented by a large classroom globe, the station would move only a few millimeters above its surface. Astronauts living there have entered space, but they have not yet entered the deepest form of it. Earth still fills their windows. Its gravity remains strong. Its magnetic field surrounds them. Radio conversations reach the ground in moments. Cargo vehicles arrive with food, tools, experiments, and messages from home. Low Earth orbit is a place between worlds. It is beyond the atmosphere as humans experience it, yet still wrapped in the influence of the planet below. The station circles Earth roughly once every 90 minutes. Each orbit carries it over oceans, deserts, clouds, cities, and storms. The crew may see 16 sunrises during a single Earth day. Light arrives quickly. Darkness follows just as quickly. The planet remains so large beneath the station that it often occupies most of the view. This closeness provides a quiet sense of orientation. There is always something below. There is always a visible home. The darkness above may feel endless, but the blue planet remains close enough to soften it. The deeper journey begins when that blue world starts becoming smaller. Earth protects life in ways that are almost invisible from the ground. The atmosphere provides air, regulates temperature, carries weather, and absorbs dangerous forms of radiation. Its clouds and winds are easy to notice because they can be seen and felt. Another form of protection surrounds the planet without color or sound. Earth possesses a magnetic field. Deep inside the planet, moving liquid iron helps generate this field through a process called the geodynamo. The magnetic field extends far beyond the surface, creating a region known as the magnetosphere. This region interacts with the solar wind. The solar wind is a continuous flow of charged particles released by the sun. It moves outward through the solar system, carrying electrons, protons, and magnetic fields across enormous distances. When these particles reach Earth, the magnetosphere redirects many of them. The field is compressed on the side facing the sun and stretched into a long tail on the night side. From a great distance, the magnetosphere would not resemble a perfect sphere. It would look more like a drop shaped by an invisible current. Life on the ground does not feel this process. There is no constant vibration. No visible wall appears in the sky. Yet charged particles are being guided around the planet every moment. Some travel toward the polar regions. There they collide with gases high in the atmosphere and create auroras. Green, red, violet, and blue light drifts above the poles. These colors are a visible trace of Earth's invisible protection. An astronaut in low orbit may see an aurora from above. It appears as a thin glowing curtain wrapped around the planet. From that perspective, the light seems delicate, but the processes creating it extend far into space. The astronaut watches charged particles meet a planetary field. Energy becomes color. The invisible becomes briefly visible. Inside low Earth orbit, the magnetic field still offers partial shelter. It does not block every energetic particle. Astronauts receive more radiation than people on the ground, but they remain closer to Earth's protective environment than crews traveling to the Moon or Mars. To move deeper is to leave more of that protection behind. The first boundary is not marked by a door. It is crossed gradually, through regions that human senses cannot detect. A spacecraft may pass from one magnetic environment into another, while the cabin appears completely unchanged. The lights remain steady. The air continues circulating. The crew feels no wind. Only instruments reveal that the surrounding universe has become different. Earth's magnetic field also holds regions of trapped radiation. These are known as the Van Allen belts. They contain energetic charged particles guided by the planet's magnetic field. The belts are not solid rings. They are broad, changing regions influenced by solar activity and Earth's magnetic conditions. Spacecraft traveling beyond low Earth orbit must consider them carefully. The Apollo missions crossed these regions on their way to the Moon. The spacecraft moved through them relatively quickly, following paths designed to limit radiation exposure. The astronauts did not see a glowing barrier. They did not hear a change outside. They simply traveled through an invisible environment containing more energetic particles. Radiation is difficult for human intuition because it often produces no immediate sensation. It does not announce itself like heat from a fire. It cannot always be seen like sunlight. Instruments measure it through interactions with matter. A detector records a particle. A sensor measures absorbed energy. A computer adds exposure over time. The danger depends on several factors. Particle type matters. Energy matters. Shielding matters. Duration matters. A brief passage through a region may produce a manageable dose. Remaining there for long periods would create a different problem. This makes deep space travel a question of time as much as distance. A journey to the Moon lasts days. A journey to Mars may last months. The spacecraft must protect its crew not only from one event, but from the accumulated environment of space. Cosmic rays arrive from beyond the solar system. Many are atomic nuclei moving at extremely high energies. Their paths may begin near supernova remnants or other powerful cosmic sources. They cross the galaxy. Magnetic fields bend their motion. Some eventually reach Earth. The atmosphere absorbs much of their energy before it reaches the surface. But beyond the atmosphere, they can pass through spacecraft walls and human tissue. No practical spacecraft can block every high-energy cosmic ray. Adding more shielding can help in some cases, yet heavy materials may also produce secondary particles when struck. Engineers must choose materials carefully. Water, food, supplies, and specialized plastics may contribute to protective shelters. During periods of increased solar activity, a crew may move into a more shielded area. The deeper a spacecraft travels, the more important these quiet preparations become. Space itself does not change its expression. It remains dark. The stars remain steady. The threat comes through particles too small and fast to notice directly. This is one reason deep space can feel more unsettling than a storm on Earth. A storm can be seen. Clouds gather, wind rises, rain touches the ground. Radiation offers fewer warnings to human senses. It becomes real through instruments, forecasts, and calculations. Knowledge replaces instinct. A crew must trust readings that describe an environment no one can feel. Beyond Earth's stronger magnetic protection, the solar wind becomes a more direct presence. It still cannot be felt as wind inside a spacecraft. The surrounding density is far too low, yet it fills interplanetary space. The sun continuously releases material in every direction. Most of the time, this flow remains relatively steady. At other times, the sun produces large eruptions. A coronal mass ejection can send enormous clouds of magnetized plasma into space. Solar flares can release intense bursts of energy. Energetic particles may arrive ahead of slower-moving material. Near Earth, satellites and observatories monitor the sun. Scientists study active regions and estimate whether an eruption may affect the planet. Earth's magnetosphere absorbs and redirects much of the disturbance. This can produce geomagnetic storms. Auroras may become brighter and appear at lower latitudes. Satellites may experience increased radiation. Communication and electrical systems may be affected. A crew traveling between planets would not have the same planetary shield. The spacecraft itself would become the main shelter. Solar activity would be watched continuously. If a strong particle event approached, astronauts might enter a protected area surrounded by water containers, supplies, or other shielding materials. The event would not sound like an approaching storm. There would be no thunder. No rain would strike the hull. The sun might look unchanged through a properly filtered instrument, yet particles would be moving through space, crossing millions of kilometers. The crew would wait behind shielding while invisible energy passed around them. This image feels quiet rather than dramatic. A small group rests inside a protected chamber. The spacecraft continues along its path. Outside, particles released by the sun move through the darkness. The event eventually passes. The crew returns to normal work. Deep space requires this kind of patience. Many dangers cannot be avoided through quick movement. They are managed through planning, measurement, and time. The sun itself begins to feel different as a spacecraft travels outward. Near Earth, sunlight is familiar. It warms the ground. It creates weather. It supports almost every ecosystem. Its daily rising and setting organizes human life. In space, the sun is no longer softened by the atmosphere. There is no blue sky surrounding it. The sun appears against blackness. Its light is direct and intense. Surfaces facing it may become hot. Surfaces in shadow may become extremely cold. There is no air to distribute heat naturally between them. Spacecraft use insulation, reflective coatings, radiators, and carefully controlled systems to maintain suitable temperatures. The cabin must remain stable while the outside experiences sharp contrasts. An object can be brightly illuminated on one side and hidden in deep shadow on the other. This makes visual interpretation difficult. A nearby structure may seem to vanish when it turns away from sunlight. A dark surface may become invisible against the sky. Then, with a slight change in angle, it may suddenly shine. The deeper a crew travels, the fewer familiar objects remain around them. Near Earth, satellites, stations, and the planet itself provide reference points. Farther away, almost everything visible is distant. The stars are too far to reveal ordinary movement. The spacecraft may be traveling thousands of kilometers each hour, yet the sky appears unchanged. Motion becomes something known through instruments, rather than felt through the body. There is no road passing beneath the vehicle. No air moves across its surface. No engine must remain active to maintain speed. Once a spacecraft is moving, it can continue for long periods with only occasional adjustments. Inside, the crew may feel almost completely still. Outside, the distance from Earth increases every second. This contrast can be difficult for the mind. The body senses rest. The instruments report departure. Earth begins as a world filling the window. Then it becomes a smaller sphere. The oceans remain visible. Clouds still turn across the surface. Continents become harder to distinguish. Eventually, Earth appears as a bright disk surrounded by blackness. This change is more than visual. It alters the emotional center of the journey. In low orbit, Earth lies below. On the way to the Moon, Earth lies behind. Direction begins to feel different. There is no universal up or down. The spacecraft may be oriented toward an antenna target, a star, the sun, or the direction of travel. The crew chooses practical reference points, but the mind may continue treating Earth as the natural center. As the planet becomes smaller, that center seems to move farther away. The Apollo astronauts experienced this during journeys to the Moon. They became the first humans to see Earth as a complete world hanging in space. Photographs from those missions changed the way people imagined the planet. Earth was no longer an endless landscape beneath the sky. It was a finite sphere, a small world surrounded by darkness. Apollo 8 carried humans around the Moon in 19. During the mission, the crew saw Earth rise above the lunar horizon. The image became known as Earthrise. The Moon's surface appeared gray and lifeless. Above it floated the blue and white Earth. The contrast was gentle and profound. Everything familiar existed inside that small sphere. Every ocean, every city, every language, every living person. From lunar distance, there were no visible borders, no individual roads, no voices. Human history had become a bright world against black space. This perspective can create wonder. It can also reveal how little surrounds Earth. The atmosphere appears as a thin layer. The oceans remain only because gravity holds them. Life exists within narrow temperature and chemical ranges. The planet seems strong from the ground. From deep space, it also seems delicate. The farther an astronaut travels, the more clearly Earth becomes one object among others. It is still home, but it no longer fills the universe. The Moon grows larger ahead. Earth grows smaller behind. The spacecraft moves between two worlds, surrounded by a region where no person can survive without machinery. The cabin becomes the entire habitable environment. Its air has been carried from Earth or produced and recycled through onboard systems. Its temperature is artificial. Its pressure is maintained by walls. Its water is limited and carefully managed. Human life continues, because the spacecraft recreates a small piece of planetary stability. Beyond the hull, there is no breathable atmosphere waiting nearby. This is where deeper space begins to feel more severe. Not because something is hiding there, because almost nothing is there at all. Interplanetary space contains particles, radiation, magnetic fields, dust and sunlight. But compared with Earth, it is nearly empty. A person cannot step outside without a suit. A broken window cannot be opened for fresh air. A crew cannot land anywhere simply because they wish to stop. Every destination is separated by enormous distance. The spacecraft is not moving through a landscape. It is carrying its own landscape. Air, warmth, water, light, and human voices travel together inside a narrow structure. The farther it moves from Earth, the more complete its isolation becomes. Radio communication still provides connection, but even radio cannot make distance disappear. A signal travels at the speed of light. This is the fastest known speed in the universe. Near Earth, the delay is almost unnoticeable. From the Moon, a message takes a little over 1 second to travel each way. A short pause appears in conversation. It is small, yet meaningful. A question is asked. Silence follows. Then the answer returns. On the way to Mars, the delay becomes far longer. Depending on the positions of the planets, one-way communication may take several minutes or more than 20 minutes. A normal conversation becomes impossible. A crew cannot ask a question and receive immediate guidance. Every message becomes a small package sent into the past. Mission Control hears what happened minutes earlier. The crew receives an answer to a situation that may already have changed. This delay makes deep space psychologically different from orbit. The crew must become more independent. Decisions must be made locally. Problems must be understood without immediate support. Earth remains present through messages, but not through conversation. The silence between transmissions grows wider with distance. That silence does not mean abandonment. It is simply physics. Radio waves cross space as quickly as nature allows, but the universe is larger than speed can easily overcome. This may be the deepest source of unease. Human technology can travel farther. It can move faster. It can survive harsher environments. Yet distance continues setting the rhythm. There is no instant return, no immediate answer, no quick journey home. The farther a spacecraft travels, the more every decision becomes part of a long path already taken. The astronaut looks back toward Earth. The planet is smaller now. Its light remains bright enough to find easily. It does not twinkle. It hangs steadily against the darkness. The spacecraft continues outward. Nothing follows it. No unknown shape moves between the stars. No signal calls from beyond the Moon. Only Earth becomes more distant, while the protective layers that once surrounded the crew remain behind. The atmosphere is behind. The strongest magnetic shelter is behind. Immediate conversation is slowly being left behind. Ahead lies a quieter environment. The deeper journey is not frightening because it is filled with visible threats. It feels more uncertain because familiar protection becomes thinner. The spacecraft carries only what its designers expected it to need. The crew depends on systems that cannot be replaced easily. The destination remains far away, and yet, within the cabin, the lights remain warm. Air continues moving. The crew continues working. A small world travels inside the larger darkness. The astronaut rests beside a window. Earth glows behind the spacecraft. The sun shines from another direction. Stars fill the remaining sky. For the first time, no planet occupies most of the view. There is only distance. The astronaut watches Earth without fear, but its shrinking shape reveals a quiet truth. The farther humanity travels, the less the universe resembles home, and every kilometer beyond Earth asks the spacecraft to become home in its place. The Moon does not appear large at first. From Earth, it seems bright and familiar. Its face has been watched for thousands of years. Dark plains form gentle patterns across its surface. Craters remain visible through small telescopes. Its changing phases divide months and guide calendars. But during a journey toward it, the Moon gradually becomes a world. The bright disk grows. Individual regions become clearer. Dark volcanic plains spread across one side. Lighter highlands surround them. Craters overlap older craters, preserving impacts from a distant age when the solar system contained more loose debris. The Moon has almost no atmosphere. There is no weather to soften its surface. No rain erases old marks. No wind moves dust across the plains. Many features remain for millions or billions of years. A crater formed long before human history may still look sharp beneath the sunlight. This gives the moon an ancient stillness. Earth changes constantly. Clouds form and disappear. Rivers move sediment. Plants grow. Ice advances and retreats. Cities spread across landscapes. The moon changes far more slowly. Its surface holds a longer memory. As the spacecraft approaches, the familiar object in the night sky becomes a quiet landscape without air, oceans, or sound. The moon's gravity is weaker than Earth's. It is strong enough to hold the moon together and guide spacecraft around it, but too weak to preserve a dense atmosphere over geological time. Gas particles move freely from the surface. Sunlight heats them. The solar wind pushes against them. Many eventually escape into space. A very thin collection of atoms and molecules still surrounds the moon. This is called an exosphere. It is so sparse that the particles rarely collide. It does not behave like the atmosphere around Earth. There are no clouds, no ordinary winds, no blue sky. From the lunar surface, the sky remains black even during the day. Sunlight falls directly onto the ground. Shadows become deep. A rock illuminated by the sun may appear bright while the region beside it becomes almost completely dark. Without atmospheric scattering, light does not fill shadows gently. This creates sharp boundaries. A ridge can divide brightness from darkness with remarkable precision. For astronauts, these lighting conditions affect movement and judgment. A small depression may disappear inside shadow. A slope may be difficult to estimate. The surface can look flat until sunlight reveals its texture. Distance also becomes harder to judge. On Earth, haze helps separate nearby objects from distant ones. The moon offers no haze. A hill far away may look almost as sharp as a rock nearby. The eyes search for clues that are no longer present. Once again, instruments and training must support human perception. The spacecraft approaches the moon's gravitational influence. There is no sudden moment when Earth's gravity stops and lunar gravity begins. Both worlds pull on the spacecraft continuously. The strength and direction of those pulls change throughout the journey. Navigation teams calculate the path carefully. Small corrections made early can determine whether the spacecraft passes too high, too low, or enters the intended orbit. The crew does not feel the changing balance directly. Inside the cabin, objects remain weightless. A pencil floats, a strap drifts, water stays inside sealed containers. The spacecraft may be moving into orbit around another world, yet the body senses almost nothing. Only the view reveals the transition. The moon grows larger, Earth grows smaller. The two worlds exchange visual importance. Then the spacecraft begins traveling around the moon. The near side has always faced Earth. The moon rotates once during each orbit around the planet. This synchronization keeps nearly the same hemisphere pointed toward Earth. The far side remained unseen by human eyes until spacecraft photographed it. It is not permanently dark. It receives sunlight just as the near side does, but it always faces away from Earth. When astronauts pass behind the moon, the planet disappears. The change happens gradually. Earth moves toward the lunar horizon. Its blue sphere approaches the gray edge of the moon. For a while, the two worlds share the window. Then Earth touches the horizon. Part of it vanishes. Oceans disappear first. Clouds become a narrowing arc. The final blue line slips behind the lunar surface. Earth is gone. At nearly the same moment, direct radio communication becomes impossible. The moon blocks the path between the spacecraft and Earth. Radio waves travel in straight lines through space. They cannot curve freely around a world large enough to obstruct them. The speaker becomes quiet. Mission control is still present on Earth. Antennas remain pointed toward the sky. Controllers continue watching clocks and predicted trajectories, but the moon lies between them and the spacecraft. No immediate message can cross the rock. For the crew, this is a scheduled silence. Everyone knows when it will begin. Everyone knows approximately when it will end. The spacecraft has been prepared to operate independently during the interval. Navigation systems continue working. Life support continues working. The crew follows planned procedures. Nothing has failed, yet the silence feels different from an ordinary pause. Earth has not merely become quiet, it has become hidden. Every human voice lies beyond the moon. Every city, ocean, forest, and family exists behind a world with no air. The astronauts become the farthest isolated human beings of their time. No person on Earth can see them directly. No one can hear them. For several minutes, the crew and the planet occupy two separate regions of space. The experience remains calm. The cabin lights do not change. Fans continue moving air. Displays continue showing numbers. The spacecraft follows its path according to gravity and momentum. Still, the absence of Earth creates a deep psychological contrast. A connection that had always been available has temporarily ended. The crew must trust the spacecraft. The ground must trust the crew. Both sides wait for the moon to release the signal again. Outside the window, the lunar far side passes below. It looks different from the familiar face seen from Earth. The far side contains more highlands and fewer large dark plains. Its surface is heavily cratered. Impact basins overlap one another. Some craters contain central peaks created when the ground rebounded after enormous collisions. Others stretch across hundreds of kilometers. The South Pole Aitken Basin is one of the largest known impact structures in the solar system. It extends across a vast region of the lunar far side. The basin formed when a large object struck the moon billions of years ago. The energy reshaped the crust. Material from deeper layers may have been exposed. Future missions study this region because it may preserve information about the moon's interior and early history. From orbit, the basin does not appear as a single simple whole. Its scale is too large. The spacecraft passes above a broad landscape formed by an event almost beyond imagination. There is no smoke remaining, no glowing rock, no sound, only geography. Time has cooled the violence into structure. This is common throughout the solar system. Many worlds carry the remains of ancient impacts. Mercury is covered with craters. Mars holds enormous basins. Moons around the outer planets display fractured surfaces and circular scars. The early solar system was more crowded with moving material. Small worlds and fragments crossed one another's paths. Collisions built some objects and broke others apart. The calm surfaces visible today preserve that earlier motion. The farther a spacecraft travels, the more clearly it encounters time. Earth's active surface hides much of its oldest history. The moon keeps more of it exposed. A crater below the spacecraft may be older than almost every rock visible on Earth's surface. The astronaut looks through the window. Nothing moves on the ground. There are no rivers, no animals, no drifting clouds. A mountain casts a shadow that may remain nearly unchanged throughout the passage. The stillness is complete enough to feel almost artificial. Yet it is simply the natural result of a world without weather. The astronaut imagines descending toward the surface. Landing on the far side would create a different kind of isolation. Earth would never rise above the horizon. A person standing there could not look up and see home. Radio communication would require a relay satellite positioned where it could see both the far side and Earth. Without such a relay, direct contact would remain blocked. The landscape would be quiet in a physical sense as well. Sound cannot travel through the lunar vacuum. Inside a spacesuit, an astronaut would hear breathing, fans, pumps and vibrations conducted through the suit. A boot touching the ground might create a vibration felt through the body, but no sound would spread outward across the plane. Two astronauts standing apart could not hear one another without radios. A rock falling nearby would strike the surface silently from the observer's perspective. The event would be visible, but not audible. Human experience depends heavily on sound. Footsteps confirm movement. Wind reveals open space. Echoes describe walls. On the moon, these clues disappear. The visual environment becomes dominant. A person sees motion but receives no matching sound from outside. This separation can make the scene feel unreal. A companion moves across the surface without footsteps. Dust rises without rustling. A tool falls without a distant clatter. Only radio communication restores the familiar link between movement and sound. The astronaut inside the orbiting spacecraft is not standing on the surface, yet the same silence surrounds the vehicle. Thrusters may fire outside. Gas expands into vacuum. The spacecraft changes direction. Inside, vibrations may be felt through the structure, but no engine roar travels through surrounding space. The moon passes below without making any sound. Its mountains do not create wind. Its craters produce no echo. The world remains present through light alone. The radio silence continues. The astronaut checks the mission timer. Only a few minutes have passed. They feel longer because no voice from Earth marks them. Time changes inside isolation. Without conversation, the mind notices smaller details. A ventilation fan seems louder. A display tone seems sharper. A floating cable becomes easier to see. The astronaut watches a small object drift across the cabin. It moves slowly until it touches a wall. The event is ordinary. Still, every object inside now feels more important. There is nothing beyond the spacecraft that can provide immediate help. The cabin has become the full human environment. This thought does not create panic. Training has prepared the crew for independent operation, but it reveals the meaning of distance. On Earth, help may be nearby even when unseen. A neighboring room contains another person. A road connects to a town. A radio connects to emergency services. Behind the moon, every human support system lies hundreds of thousands of kilometers away. Even after communication returns, no rescue can arrive quickly. A crew must solve most immediate problems using what is already on board. This is true throughout deep space. Distance turns preparation into survival. Spare parts matter. Redundant systems matter. Clear procedures matter. Knowledge matters. A small tool may be more valuable than an object of great price on Earth because no replacement is close. A container of water is not only a drink, it may support cooling, hygiene, food preparation, and radiation protection. A sealed volume of air is not ordinary atmosphere. It is a carefully maintained resource. The farther a spacecraft travels, the more every familiar material gains meaning. Nothing is easily replaced. Nothing can be wasted casually. Deep space does not make matter more rare in the universe. It makes useful matter less accessible to the crew. The moon contains rock, metals, and frozen water in some shadowed regions. But these materials are not immediately available. They must be located, extracted, processed, and transformed. A spacecraft cannot drink lunar ice simply because it exists. Technology must create the path between resource and need. Future lunar bases may use local materials. Water ice near the poles could provide drinking water, oxygen, and hydrogen. Lunar soil might help shield habitats from radiation. Metals and minerals could support construction. This approach is called in situ resource utilization. It means using materials found at the destination rather than carrying everything from Earth. For long missions, this may become essential. A settlement that depends entirely on deliveries remains fragile. A settlement that produces some of its own water, air, fuel, or building material becomes more independent. The moon may serve as the first place where humanity learns this deeply. It is close enough for communication and travel compared with Mars. Yet it is far enough to expose the difficulties of living beyond Earth. There is no breathable air. Radiation is stronger. Temperatures vary greatly. Dust is fine, abrasive, and electrically active. The lunar day lasts about 2 Earth weeks. The lunar night lasts about 2 Earth weeks. Solar power becomes difficult during long darkness unless energy is stored or generated another way. Every ordinary human need becomes an engineering question. How is heat maintained? How is air cleaned? How is water recycled? How is dust kept away from seals and machinery? How does a crew sleep beneath reduced gravity? How are medical emergencies managed? The moon looks simple from a distance. Up close, survival becomes a network of systems. The astronaut thinks about lunar dust. It formed through billions of years of impacts. Without weather to smooth the grains, many particles remain sharp and irregular. Solar radiation and the solar wind can charge the surface electrically. During the Apollo missions, dust clung to suits and equipment. It entered the lunar modules. Astronauts described its smell after it was brought into the pressurized cabin, although the dust itself could not carry an odor through vacuum. The smell may have come from chemical reactions occurring when fresh lunar particles met oxygen and moisture inside the spacecraft. The dust caused practical concerns. It could scratch surfaces. It could affect seals. It could irritate eyes and lungs if allowed to circulate. Future missions must control it carefully. This is another way deeper space becomes less forgiving. A quiet material beneath the boots can become a challenge simply because Earth's natural processes are absent. Rain does not wash the dust away. Wind does not round its edges. Soil organisms do not transform it. The lunar surface remains chemically and physically unfamiliar. Nothing there evolved beside human lungs or skin. The spacecraft continues behind the moon. The crew cannot see Earth, but they can still predict its position. Navigation does not depend on sight alone. Stars provide references. Gyroscopes track orientation. Computers model the spacecraft's path. Radio ranging before and after the blackout helps refine the orbit. The moon's gravity is not perfectly uniform. Large concentrations of mass beneath some lunar basins create regions called mascons. These can slightly alter spacecraft trajectories. Early lunar missions discovered that orbits around the moon could change unexpectedly if these variations were not included accurately. Modern navigation models account for them. The moon appears still, but its gravity contains structure. Dense material hidden beneath the surface pulls a little more strongly. The spacecraft responds. Again, instruments reveal what the eyes cannot. The astronaut sees craters. The navigation computer feels mass. Deep space becomes understandable through layers of measurement. Visible landscapes are only one part of the environment. Gravity maps reveal interiors. Spectrometers reveal chemistry. Radar reveals buried structures. Radiation detectors reveal particles. Seismometers reveal movement beneath the ground. Human senses offer an opening. Technology expands it. A small indicator changes on the communication panel. The spacecraft is approaching the point where Earth will return. The crew prepares to transmit stored information. Status reports have been recorded during the blackout. System readings are ready. Navigation data has been checked. Nothing unusual occurred. The silence will end exactly as planned. The lunar horizon moves across the window. At first, only stars appear beyond it. Then a blue point emerges. Earth rises from behind the moon. It begins as a thin curve. More of the planet becomes visible. White clouds appear. Blue oceans follow. The full disk slowly returns. At nearly the same moment, the radio produces static. A broken sound becomes a voice. Mission Control calls the spacecraft. The crew responds. The exchange is brief and professional. Systems are normal. The trajectory remains correct. The blackout period passed without difficulty. Yet the return of the human voice carries more meaning than the words themselves. Earth is reachable again. The planet and crew once more share a line of sight. The astronaut watches Earth above the lunar horizon. The sight feels different now. Before the blackout, Earth was simply behind the spacecraft. Afterward, it feels like something recovered. Nothing was truly lost. The planet continued turning. People continued living. Ground teams continued waiting. But temporary absence has made its presence clearer. This rhythm will repeat during every lunar orbit. Earth appears. Earth disappears. Voices arrive. Voices stop. The crew gradually adapts. The first blackout feels profound. Later ones become part of the schedule. Human beings can become familiar with remarkable conditions. A sunrise every 90 minutes becomes normal in low orbit. Earth vanishing behind the moon becomes expected. Weightlessness becomes ordinary. The unusual does not remain emotionally intense forever. The brain learns, patterns form, uncertainty decreases. This adaptation allows exploration to continue. Without it, every orbit would feel like the first. But familiarity also carries a quiet risk. An environment can become comfortable without becoming safe. The moon remains airless. Radiation remains present. Communication remains limited by geometry. The spacecraft still depends on many connected systems. Training therefore balances adaptation with attention. A familiar sound may be ignored only after it is understood. A routine procedure still requires careful completion. Calm does not mean carelessness. It means the crew can observe clearly without being overwhelmed. The spacecraft continues around the moon. Earth remains visible for now. The astronaut rests beside the window and considers what deeper travel would remove next. The moon still offers a nearby world. Its surface fills the view. Earth returns during every orbit. Radio silence lasts only minutes. A damaged spacecraft might still be days from home rather than months. Beyond the moon, these comforts begin thinning again. During a journey to Mars, no large world may fill the window for long periods. Earth becomes a bright point. Mars remains a distant point ahead. Communication never disappears completely behind one nearby object, but every message carries delay. The crew lives between planets. There is no horizon outside. No surface passes below. No world rises after a few minutes to restore contact. Only the spacecraft continues through sunlight and darkness. The lunar far side offers a brief lesson in that deeper isolation. It shows what happens when Earth becomes unavailable. For a short time, the crew experiences a universe without an immediate human voice. Then the planet returns. The lesson ends gently. The spacecraft remains secure. The mission continues. The moon's silence has not threatened the crew. It has simply revealed how much comfort arrives through connection. As the astronaut prepares to rest, Earth shines above the gray horizon. The planet looks small enough to cover with a hand, yet every known home exists there. The moon below is larger in the window, but empty of human life. Scale and importance no longer match. The larger object is not home, the smaller one is. The astronaut closes the eyes. The radio remains quiet for the moment, though communication is available. Fans move air through the cabin. The spacecraft travels onward through lunar orbit. Soon it will pass behind the moon again. Earth will disappear. The voices will stop, but the astronaut now knows what waits beyond the silence. Not abandonment, not an unknown presence, only a planet continuing along its path, ready to rise again when geometry allows. And in the darkness between those moments, the spacecraft carries its own small circle of light, warmth, and human attention around the ancient moon. Beyond the moon, the sky does not become darker. It is already black. There is no additional shade waiting farther away. No curtain closes behind the spacecraft. The same stars remain visible, scattered across the same silent background. What changes is not the darkness. What changes is the absence of nearby worlds. Near Earth, the planet fills the view. Near the moon, gray mountains and cratered plains provide scale. But during a long journey between planets, neither world remains large for very long. Earth becomes a bright point behind the spacecraft. The destination remains another point ahead. Between them lies a region measured in millions of kilometers. The spacecraft crosses it slowly. Inside the cabin, the crew does not feel that speed. There is no atmosphere outside to create resistance. No road passes beneath the vehicle. No nearby landscape reveals motion. The stars remain so distant that their positions change almost imperceptibly. A person may look through the window and feel completely still, yet every second carries the spacecraft farther from Earth. This creates one of deep space's strangest contradictions. The journey is enormous. The sensation is quiet. Motion becomes something known through numbers. A navigation screen shows distance traveled. A clock counts mission time. A computer predicts the spacecraft's future position. The body itself offers almost no evidence. It floats, it breathes, it rests inside a moving room. The crew gradually learns to trust measurements more than instinct. On Earth, movement is felt through acceleration, vibration, sound, and changing scenery. In interplanetary space, long periods may contain none of these things. An engine burns briefly. The spacecraft changes velocity. Then the engines stop. Silence returns. The vehicle continues moving, because there is almost nothing to slow it. For days or weeks, the path unfolds without another major burn. This is called coasting. The word sounds gentle. It describes a spacecraft crossing millions of kilometers while appearing almost motionless from within. The sun remains the brightest object outside. Its light enters the windows without atmospheric softness. The star itself looks smaller as the spacecraft travels outward, though the change is gradual. Near Earth, sunlight provides more energy than near Mars. Farther from the sun, the same light spreads across a larger region. Its intensity decreases with the square of the distance. A spacecraft twice as far from the sun receives only 1/4 as much solar energy. This simple relationship shapes exploration. Solar panels become less productive farther outward. Temperatures change. Instruments require different thermal designs. Missions near Jupiter and beyond may use nuclear power sources because sunlight has become too weak for practical solar systems of ordinary size. The crew traveling toward Mars still receives useful sunlight, yet the star's influence is already changing. Earth no longer filters it. The atmosphere no longer colors the sky blue. Sunlight enters from one direction, while the rest of the universe remains black. A surface facing the sun may warm. A surface turned away may cool. Inside, thermal control systems work continuously. Heat produced by people, computers, lights, and experiments must be removed. On Earth, warm air rises and carries heat away. In microgravity, natural convection behaves differently. Fans keep air moving. Pumps carry heat through fluid loops. Radiators release that heat into space. A spacecraft must lose heat carefully, even while surrounded by cold darkness. Space itself does not have a single temperature in the ordinary sense. A thermometer depends on what is transferring energy into it. In sunlight, an object may become warm. In shadow, it may radiate heat away. The surrounding vacuum cannot conduct warmth like air or water. Temperature becomes a question of radiation and material. The crew lives inside an artificial climate. Every comfortable degree is maintained by machinery. A small change in airflow can make a corner feel warm. A blocked vent can allow carbon dioxide to gather. A failed pump can affect several systems at once. This is why maintenance fills so much of a deep space mission. Exploration does not consist only of looking through windows. It consists of replacing filters, inspecting seals, checking cables, cleaning surfaces, testing backup equipment, recording small variations before they become larger problems. The farther the spacecraft travels, the less replaceable each component becomes. Near Earth, cargo vehicles can deliver new parts. Between planets, every spare item must already be on board. A damaged valve cannot be ordered from the ground and received the next day. A broken tool may need to be repaired using another tool. An unused container may become material for an unexpected solution. The crew carries not only equipment, but possibility. A spare cable may solve a future problem no one has predicted. A piece of fabric may become a restraint. A storage container may become shielding. Deep space vehicles are designed with redundancy. Several systems may be able to perform similar tasks. A primary computer has backups. Communication can use more than one antenna. Life support may contain replaceable components and emergency reserves. But redundancy has limits. Every added system increases mass. Every kilogram requires energy to launch and accelerate. Engineering becomes a careful balance between carrying enough and carrying too much. The crew lives inside that balance. Each object has earned its place through planning. Water is one of the most valuable materials on board. It supports drinking, food preparation, hygiene, cooling, and sometimes radiation shielding. Much of it is recycled. Moisture from breath enters the cabin air. Humidity control systems collect it. Wastewater is processed. Filters and chemical treatments remove unwanted material. The recovered water returns to use. The cycle is not completely closed. Some losses remain. Supplies must be managed carefully. Yet every liter used again reduces the amount that must be carried from Earth. This recycling makes the spacecraft resemble a small ecosystem. Humans consume oxygen and produce carbon dioxide. Plants, if included, may use some carbon dioxide and release oxygen. Machines complete most of the cycle. They remove carbon dioxide. They produce oxygen from water. They filter air. They reclaim moisture. The biological crew and mechanical systems depend on one another. The spacecraft is not merely transportation. It is a temporary world. Its atmosphere has boundaries. Its water has a history. Its waste becomes a resource. Its population is small. There is no river outside. No rainfall arrives. No forest renews the air. Every cycle is deliberate. The farther the vehicle moves from Earth, the more clearly this artificial world reveals what planets do naturally. Earth recycles water through oceans, clouds, rain, rivers, soil, and living things. Its atmosphere circulates gases. Its ecosystems transform waste. Its magnetic field and atmosphere provide protection. A spacecraft reproduces tiny portions of those processes using pipes, filters, pumps, and software. What appears effortless on Earth becomes visible engineering in space. The crew hears that engineering constantly. Fans hum, valves click, pumps begin and stop. These sounds become the vehicle's weather. A change in tone may reveal a change in operation. An experienced crew member can recognize when a fan is running differently. A small vibration can lead to an inspection. The spacecraft speaks through machinery. The crew learns its language. Outside, the universe remains silent. Sound cannot cross the surrounding vacuum. The spacecraft may pass near a small particle. A thruster may release gas. A solar panel may adjust its angle. None of these events produces an external sound that travels back through space. Only vibrations entering the structure can be heard inside. This makes the cabin's mechanical noise more important. It confirms that air is moving, that power is flowing, that systems remain active. Silence inside would not feel peaceful. It would require explanation. The crew does not seek complete quiet. It seeks familiar sound. Days begin to resemble one another. A schedule protects the body and mind. The crew wakes according to the mission clock. Lights brighten gradually. Health measurements may be recorded. Breakfast is prepared from packaged food. Work begins. Experiments are monitored. Maintenance tasks are completed. Exercise occupies a significant part of the day. Without gravity loading the body, muscles and bones begin changing. Resistance machines imitate weight. Treadmills use harnesses to pull the body toward the moving surface. Stationary bicycles support cardiovascular health. Exercise does not restore gravity. It provides the body with a reason to remain strong. The routine can feel repetitive. That repetition is valuable. It divides a vast journey into manageable days. Mars may still be months away. Earth may already be millions of kilometers behind. But the next task is close. A filter must be checked. A meal must be prepared. A message must be recorded. A scientific sample must be photographed. Human attention works better when distance is converted into activity. The journey becomes not one enormous waiting period, but thousands of smaller actions. The crew also needs private time. A deep space vehicle may offer little personal space. Sleeping compartments provide some separation. Headphones create another kind. Messages from family allow connection with Earth, though delays increase throughout the journey. At first, the delay is only seconds. Then it becomes minutes. A recorded message leaves the spacecraft. The crew continues working. Much later, the message reaches Earth. A reply begins its own journey back. By the time it arrives, the original moment has passed. A person may describe a difficult day and receive comfort after the difficulty has already faded. The answer still matters. It simply belongs to a different rhythm. Communication becomes correspondence rather than conversation. Letters once crossed oceans over weeks or months. Deep space messages restore something similar, using light. The information moves far faster than any ship, yet the distance remains large enough to create patience. The crew begins speaking differently in recorded messages. More context is included. Questions are chosen carefully. Several topics may be combined. Silence is anticipated. A message becomes complete enough to stand alone. This change affects mission control as well. Controllers cannot guide every action in real time. They send procedures, analysis, and recommendations. The crew uses them when they arrive. Responsibility gradually moves toward the spacecraft. Deep space exploration requires trust in both directions. Earth trusts the crew to make good decisions. The crew trusts Earth to provide careful support despite delay. Neither side controls the other completely. Distance creates independence. Outside the window, Earth eventually becomes difficult to distinguish from nearby stars. It remains brighter than many of them, but its shape can no longer be resolved by the unaided eye. The planet that once filled the view is now a point. All its oceans have collapsed into one small light. Clouds cannot be seen. Continents have disappeared. The moon may appear beside it as a much fainter companion. From this distance, the entire Earth-Moon system occupies a tiny region of the sky. The astronaut knows exactly where to look. Navigation software provides the direction. A camera with magnification can reveal more, but the naked eye sees only light. This is the moment when home becomes astronomical. Earth no longer resembles a place. It resembles an object studied from afar. The emotional effect can be profound. Every familiar location is still there. A childhood street, a mountain, a kitchen table, a crowded city, a quiet bedroom. Yet none can be separated from the single point. The astronaut is physically farther from every human being than almost anyone in history. Still, Earth remains connected through radio. Its gravity continues influencing the spacecraft, though weakly. Its light continues crossing the distance. Home has become small, but not absent. The crew may photograph it. The image resembles the pale blue dot captured by Voyager 1 in 1990. That spacecraft looked back toward Earth from billions of kilometers away. The planet appeared as a tiny point suspended in a beam of scattered sunlight. The photograph revealed no geography. Earth occupied less than a single pixel, yet that point contained every known person and every known living world. The image became powerful because scale had removed almost everything except meaning. A deep space crew sees the same lesson developing in real time. The planet becomes visually smaller while emotionally remaining immense. The farther it recedes, the more clearly it appears as one shared place. The spacecraft continues toward Mars. The destination slowly brightens. At first, Mars is only another reddish point. Its color comes largely from iron minerals on its surface that have oxidized over time. The planet appears red, because dust rich in iron compounds covers much of its landscape. As the spacecraft approaches over many weeks, Mars grows from a point into a disk. But during the middle of the journey, neither Earth nor Mars looks like a world. The crew lives between two lights. This region has no natural human name, comparable with ocean or desert. It is interplanetary space. The phrase describes an environment defined by separation. Planets occupy only a tiny portion of the solar system's volume. Most of the region between them contains extremely thin plasma, magnetic fields, dust, and radiation. The solar system is not crowded with worlds. It is mostly distance. Diagrams often place planets close together so they can fit on a page. Their sizes are enlarged. Their orbits are compressed. In reality, the emptiness dominates. If the Sun were reduced to the size of a large ball, Earth would be a small bead many meters away. Mars would be farther still. The region between them would contain almost nothing visible. A spacecraft crossing that model would be smaller than dust. This scale reduces the imagined danger of collision with a planet or large asteroid. Space is wide enough that missions must aim carefully to reach anything at all. But small particles remain a concern. Micrometeoroids move through the solar system. They may be fragments of comets or asteroids. Most are tiny. A grain of dust can still carry significant energy if the relative speed is high. Spacecraft use protective layers. A thin outer shield may break a particle apart. The fragments spread before reaching the main pressure wall. This design is often called a Whipple shield. It transforms one concentrated impact into a wider, less damaging spray. The crew may never know when a microscopic particle strikes. The impact may leave a tiny mark outside. Sensors may record a vibration. Most events produce no noticeable effect. Again, protection works quietly. The spacecraft is surrounded by many small defensive decisions. Layers, spacing, material choices, angles, redundancy. Deep space feels severe because mistakes may carry greater consequences. Yet it is also filled with systems designed to prevent those consequences. The crew does not travel inside a fragile shell chosen casually. The vehicle is the result of years of testing. Materials have been exposed to vacuum. Components have been shaken. Electronics have been tested against radiation. Software has been reviewed. Failure scenarios have been simulated. No design can remove all uncertainty, but uncertainty has been considered. The astronaut looks through the window during a rest period. No planet fills the view. Earth lies behind as a small light. Mars remains ahead as another. The sun shines from one side. Stars surround everything. For the first time, the spacecraft feels truly between worlds. There is no surface nearby. No orbiting station. No large moon crossing the window. Only the vessel and the distance. The astronaut notices a faint point moving slowly against the stars. It may be a small particle close to the window. It may be an internal reflection. The point drifts for several seconds and fades. No concern follows. The crew has learned to separate observation from imagination. A moving light does not need a purpose. A brief signal does not need a sender. Interplanetary space contains matter. Sunlight reveals it temporarily. Then geometry carries it away. Still, the sight creates a quiet thought. If another spacecraft were crossing the solar system, it might appear exactly this small. A single point, no shape, no sound, no obvious scale. Humanity's own probes travel through deep space this way. They move silently between worlds. Most are far too small and distant to see without precise instruments. Mars orbiters circle the red planet. Other probes visit asteroids. Some move toward Jupiter. Voyager travels through interstellar space. Each carries the work of human minds into regions where no person is present. From a great distance, a human spacecraft would not look impressive. It would be a faint object, absorbing and reflecting light. Its intelligence would exist not in appearance, but in behavior. It would correct its path, point an antenna, gather data, transmit patterns. Intention becomes visible through repeated action. The same would be true of an unfamiliar machine. One strange movement would prove little. A consistent pattern might matter more. The astronaut watches the faint point until it disappears. Nothing changes. The spacecraft continues. The crew returns to work. Between worlds, even mystery must share space with routine. Hours later, The astronaut enters the sleeping compartment. The body is secured gently against the wall. Air moves near the face. The familiar mechanical weather fills the narrow space. Outside, the spacecraft crosses a region with no name on any ordinary map. Earth is too far behind to appear as home. Mars is too far ahead to appear as a destination. The vehicle carries the only breathable air for millions of kilometers. This fact is clear. It is not overwhelming. The crew has lived inside the system long enough to trust its rhythms. The deepest uncertainty does not come from something approaching through the dark. It comes from the scale of the space itself. Distance delays every answer. Distance enlarges every journey. Distance turns a planet into a point. Yet the same distance also creates calm. There is room between worlds. No crowded sky surrounds the spacecraft. No alien form waits beside the hull. Only sunlight, dust, particles, fields, and the steady movement of one small human world toward another. The astronaut closes the eyes. Earth continues shrinking behind the spacecraft. Mars continues growing ahead. Neither change can be felt. Both are happening. And in the wide silence between them, the crew learns that deep space is not empty of meaning. It is simply too large to reveal everything at once. The warning begins as a change in data. No cloud appears outside. No light flashes across the window. No vibration passes through the spacecraft. The sun looks almost unchanged. Yet instruments near Earth have detected an eruption. A large region of the solar atmosphere has released energy. Magnetic fields have twisted, stretched, and rearranged themselves. Heated plasma has been thrown outward into space. The event is called a coronal mass ejection. It carries billions of tons of charged material away from the sun. Its path may spread across a wide region of the solar system. Sometimes it misses every inhabited spacecraft. Sometimes it moves in another direction. Sometimes its expanding cloud crosses the path of a crew traveling between planets. The warning reaches the spacecraft through radio. The message was sent several minutes earlier. It describes an event that has already happened near the sun. Scientists on Earth study images from solar observatories. They compare measurements from satellites positioned at different locations. They estimate the speed, direction, and magnetic structure of the eruption. The crew receives a probability. The particle environment may become stronger. A period of increased radiation may arrive later. The time remains uncertain. Solar eruptions do not travel at the speed of light. The first warning can come from electromagnetic radiation, which crosses space much faster than the particles themselves. This provides preparation time. Sometimes only a short interval is available. Sometimes the crew may have many hours. The spacecraft continues quietly toward Mars. Nothing outside reveals that part of the sun is sending material across interplanetary space. The black sky remains black. The stars remain steady. The astronaut reads the message twice. There is no immediate emergency. There is a procedure. The crew begins preparing the more protected region of the spacecraft. Water containers are positioned around it. Food packages and supplies add more mass between the crew and the outside. The shelter is not a separate armored room. It is often an ordinary part of the vehicle arranged to provide additional shielding when necessary. Hydrogen-rich materials are useful against many charged particles. Water contains hydrogen. Certain plastics contain it as well. These materials can slow particles while producing fewer harmful secondary fragments than some heavier metals. The spacecraft already carries water and supplies. Their location can be chosen carefully. Objects needed for life become part of the protective structure. The crew checks the shelter. Communication equipment is available. Medical supplies are nearby. Airflow remains clear. The temperature is monitored. Nothing blocks the entrance. The preparation is calm. A checklist turns an invisible event into a sequence of simple actions. Secure loose objects. Confirm detector operation. Review the forecast. Move required supplies. Reduce unnecessary activities. Wait. Waiting is part of deep space travel. A spacecraft cannot outrun a large solar eruption once it is nearby. The crew cannot steer around it easily. The affected region may stretch across millions of kilometers. Protection depends on shielding and time. The particles arrive. They pass. The crew remains inside. The sun creates weather without air. On Earth, weather exists within an atmosphere. Heat drives winds. Water forms clouds. Pressure differences create storms. In space, solar weather is shaped by plasma and magnetic fields. The solar wind flows outward continuously. It carries the sun's magnetic influence through the solar system. A coronal mass ejection disturbs this flow. Its magnetic field can compress, twist, and interact with the fields around planets. Near Earth, the magnetosphere responds. Its sunward side is pressed inward. Its long tail becomes disturbed. Charged particles enter regions where they produce brighter auroras. The planet absorbs much of the event through its atmosphere and magnetic environment. A crew between planets has no planet surrounding it. The spacecraft becomes the nearest shield. This is where deeper travel changes the meaning of a solar storm. Near Earth, the event is partly a problem for satellites, electrical systems, radio communication, and astronauts already above the atmosphere. On the ground, most people remain protected. Between planets, the crew is part of the forecast. Every estimate becomes personal. What energy will the particles carry? How long will the event last? How much shielding surrounds the shelter? What dose may reach the body? Radiation is measured carefully. A dosimeter records absorbed energy. Several detectors may be placed around the spacecraft. Their different locations reveal how structure changes exposure. A detector behind water may show less activity. Another near the outer wall may respond more strongly. The spacecraft becomes a small laboratory within the storm. The first increase appears on a screen. A line rises above its recent background. The change is modest. Then another detector responds. The crew enters the shelter. Inside, the space is narrow. Shoulders float near storage bags. Knees bend because there is little room to extend the body fully. The crew does not need gravity to sit together. Handholds and soft restraints keep everyone positioned. A screen displays the particle measurements. The cabin lights remain warm. The ventilation fan continues its familiar sound. Outside, charged particles move through the spacecraft. Most pass through the outer structure or lose energy within it. Some collide with atomic nuclei in the shielding. These collisions can create secondary particles. The radiation environment is not a simple rain striking one surface. Particles arrive at different energies and directions. Materials change them. Some are absorbed, some scatter, some produce smaller fragments. Designing protection requires detailed physics. No wall can make the universe disappear completely. The goal is to reduce exposure to acceptable levels. The crew waits. A message arrives from Earth. The ground team has received more measurements. The event appears stronger than first predicted, but the shelter remains adequate. The message itself crossed the distance while the particles continued moving. Radio travels faster. Information reaches the crew before the densest part of the event. This is one of the few advantages distance can provide. The sun announces the storm with light before the slower particles arrive. Yet forecasts remain difficult. Solar eruptions change as they travel. They interact with the surrounding solar wind. Their magnetic orientation matters. Two events may merge. A faster eruption may catch a slower one. The resulting structure becomes more complex. Scientists reconstruct this invisible motion using instruments spread across the solar system. One spacecraft observes the sun. Another measures particles near Earth. Another near Mars records the changing solar wind. Each contributes a limited view. Together, the measurements create a moving map. The astronaut watches the radiation line rise again. Nothing can be felt. The body offers no warning. There is no pressure against the skin, no change in breathing, no smell. Only the detector shows that the surrounding environment has become more energetic. This difference between sensation and reality can feel unusual. On Earth, many dangers announce themselves. Smoke reveals fire. Heat warns the skin. A loud sound suggests impact. Radiation can pass unnoticed. Humanity learned to measure it only through instruments. Deep space therefore requires trust in things the senses cannot confirm. A detector becomes an extra sense. A number becomes part of the environment. The astronaut does not need to imagine particles individually. There are too many. Some are protons. Some are heavier atomic nuclei. They move quickly enough to cross the spacecraft in fractions of a second. A single particle may pass through a wall, an equipment rack, and living tissue before continuing outward. Most interactions produce no noticeable effect. The concern comes from accumulated energy deposited in cells. Radiation can damage molecules. Cells may repair much of this damage. Sometimes they cannot. The risk depends on dose, duration, particle type, and which tissues are exposed. Deep space missions must manage this risk over months and years. A short solar event is only one part of the total. Galactic cosmic rays form a continuous background. They arrive from beyond the solar system. Their energies can be extremely high. Solar activity can influence how many reach the inner solar system. A strong solar wind and active magnetic environment may reduce some lower energy cosmic rays. This creates a complicated balance. When solar activity is high, solar particle events may become more likely. When solar activity is low, more galactic cosmic rays may enter the inner solar system. There is no season with no radiation at all. Mission planning chooses among changing conditions rather than waiting for perfect safety. The crew remains in the shelter. One astronaut records a message for family. It will not be sent immediately. Communication bandwidth is being reserved for mission data. The message can wait. It describes the situation calmly. The crew is protected. The storm is being monitored. The spacecraft is working normally. The astronaut pauses before ending. From Earth, the word storm may create images of wind and rain. This event has neither. The message explains that nothing dramatic can be seen. The crew is simply spending several hours inside a more shielded part of the vehicle. Perhaps that ordinariness is the strangest detail. A powerful event crosses the solar system. Humans respond by moving water containers, checking screens, and waiting beside one another. Deep space often reduces enormous physics into small practical actions. The sun rearranges magnetic fields larger than Earth. A crew closes a hatch. Billions of tons of plasma move outward. A detector counts particles. The solar system changes. A checklist receives another mark. The contrast makes the crew's work feel both small and meaningful. The spacecraft cannot control the sun. It can control preparation. Hours pass. The radiation level reaches a broad maximum. Then it begins declining. The change is slow. The crew remains inside until specialists confirm that leaving the shelter is appropriate. There is no exact moment when the storm ends. The environment gradually returns toward its previous background. Particles continue passing through space. Only their number and energy distribution change. The crew waits a little longer. Patience adds safety. The astronaut looks at the shelter's walls. They are not thick in the way a stone building is thick. Storage bags cover part of the surface. Water containers sit nearby. Equipment occupies the remaining space. The arrangement seems improvised, but every element has been considered. Deep space protection often depends on using ordinary materials in several ways. Water is life support and shielding. Food is nutrition and mass. Waste may also provide shielding if stored safely. Fuel surrounds some spacecraft regions. Machinery adds structure. The vehicle's layout becomes part of survival. Future Mars missions may include shelters placed near the center of the spacecraft. Supplies could form a protective ring. Sleeping quarters might be arranged where shielding is naturally strongest. Advanced materials may reduce exposure further. Some concepts use magnetic or electric fields to redirect charged particles, though creating practical systems would be challenging. Every approach must balance power, mass, reliability, and effectiveness. The problem is not unsolvable. It is simply persistent. The radiation line continues falling. The crew eventually leaves the shelter. The cabin outside appears unchanged. The same lights glow. The same handrails cross the walls. The same small objects remain secured. No dust has entered. No burn mark appears on the hull. The storm passed through matter rather than around it. The astronaut floats toward a window. The sun remains bright. It does not appear more active to the unaided eye. Viewing it directly would be unsafe, so instruments and filters provide the useful images. A display shows the solar eruption from hours earlier. An enormous bright structure rises from the sun's edge. Loops of plasma follow magnetic fields. Material expands outward. The scale is difficult to understand. Earth could fit inside some solar features many times. Yet the sun itself is only one star. Other stars produce eruptions far more energetic. Some young stars are highly active. They release frequent flares. Planets orbiting them may experience intense radiation. This matters when scientists consider life elsewhere. A planet may lie at a distance where liquid water could exist, but its star's activity may shape the atmosphere and surface. Strong radiation could remove atmospheric gases over time. It could also drive chemical reactions. A magnetic field might offer protection. A thick atmosphere might absorb energy. Life, if present, might remain underwater or underground. The relationship between a planet and its star becomes part of habitability. Earth is not suitable for life only. because of distance from the sun. It also has an atmosphere, magnetic environment, water, geology, and a long history of changing conditions. Deep space travel reveals how many layers of protection life normally receives without noticing. The astronaut watches the solar image. The eruption is beautiful. It appears as light and structure rather than threat. The danger came from particles and energy. The image shows the same event as flowing plasma shaped by magnetism. Fear and wonder can describe the same process from different positions. From inside the shelter, the storm was a calculation of exposure. From a solar observatory, it is a vast movement of luminous material. Neither view is complete alone. Science holds both. The crew spends the following day checking equipment. Some electronics have recorded small errors. Radiation can alter digital memory. A charged particle may pass through a transistor and change its state. This is called a single event upset. The effect may resemble a tiny mistake inside stored information. Spacecraft systems use error correction, redundancy, and protective design to reduce the consequences. Most errors are detected and repaired automatically. One instrument requires a restart. Another has stored incomplete data during the strongest part of the event. No critical system has failed. The storm leaves only small traces, a few changed bits, a temporary detector increase, several hours spent in shelter. The event that crossed millions of kilometers has become a maintenance note. The astronaut reflects on how much of exploration depends on invisible preparation. The public may see launches, planets, and photographs. The crew experiences filters, schedules, software checks, and radiation forecasts. The spectacular journey is carried by ordinary discipline. This is what allows calm to exist far from Earth. The spacecraft is not fearless. It is prepared. The crew does not assume the universe is gentle. It learns its patterns and builds responses. As the vehicle continues toward Mars, the solar storm moves outward. Its expanding structure travels toward the outer planets. It becomes weaker and more dispersed, yet it may remain measurable far from the Sun. Spacecraft elsewhere may detect it later. A probe near Jupiter might record a disturbance. Another instrument farther away may encounter its fading edge. The storm becomes a message carried through plasma. It reveals how the Sun influences a region extending far beyond the planets. This region is called the heliosphere. The solar wind creates it as it flows into interstellar space. The heliosphere surrounds the solar system like a vast, changing bubble. Its exact shape depends on the Sun's motion through the galaxy and the pressure of surrounding interstellar material. The planets travel inside it. Human spacecraft travel inside it. Even at Mars, the crew remains within the Sun's extended environment. Deep space has not yet become truly interstellar. The Sun still surrounds the mission through particles and magnetic fields. The astronaut had once imagined the deeper journey as movement away from everything. The solar storm reveals a different truth. The spacecraft is still connected to its star. Sunlight reaches it. Solar wind passes it. Eruptions cross its path. The Sun's influence stretches far into the darkness. Distance does not create complete separation. It changes the form of connection. Earth has become a small point. The Sun remains a powerful presence. Farther outward, even that presence will weaken. The solar wind will eventually slow as it meets the material between stars. Voyager spacecraft have crossed boundaries where the solar environment changes dramatically. Beyond lies interstellar space. There, the Sun becomes one distant star among others. The astronaut is not traveling that far. Mars remains the destination. Still, the thought of those greater distances returns. If a solar storm can take hours to cross the crew's path near the inner planets, what happens where the Sun's protection fades? Galactic cosmic rays become more important. The familiar star becomes smaller. Communication delays grow. Power becomes harder to collect from sunlight. Every layer of distance removes another familiar advantage. Yet exploration advances one boundary at a time. A lunar mission does not need to solve interstellar travel. A Mars crew does not need to cross the heliosphere. Each journey learns what the next may require. Radiation shelters tested near Earth inform deeper missions. Water recycling developed in orbit supports travel between planets. Navigation around the Moon prepares crews for distant worlds. Human progress is modular. It builds one protected room inside another. The astronaut returns to the sleeping compartment. The solar storm is now behind them. Detectors have returned to normal levels. Earth has received the mission report. Family messages will arrive later. The spacecraft continues coasting. The body floats inside the sleeping bag. The ventilation fan moves air gently across the face. Outside, the particles of the storm continue away from the sun. They spread through a volume too large to see. No sound follows them. No mark remains in the sky. The event is already becoming data. The astronaut closes the eyes. Deep space has become more severe, but also more understandable. The storm was invisible. It was not unknowable. It could be detected, forecast, measured, managed. The farther humanity travels, the more it must trust instruments, preparation, and one another. And inside the quiet shelter of the spacecraft, even the restless sun becomes another pattern that can be watched until it passes. Mars does not remain large for long. A spacecraft may approach the planet, enter orbit, release a lander, or use its gravity to change direction. For a while, the red world dominates the windows. Dusty plains stretch beneath thin clouds. Dark volcanic regions cross the surface. The canyon system of Valles Marineris cuts through the landscape for thousands of kilometers. Olympus Mons rises higher than any mountain on Earth. The planet appears enormous when viewed from nearby orbit. Then the journey continues. Thrusters fire. The spacecraft changes its path. Mars begins shrinking behind it. At first, the planet remains a clear disk. Its polar ice is visible. Its atmosphere forms a narrow line around the edge. Then surface features fade. The planet becomes a reddish circle. Later, it becomes another point among the stars. A world that filled the view is reduced once again to light. The spacecraft is now moving beyond the orbit of Mars. Sunlight grows weaker. The sun still appears brilliant, but it occupies a smaller region of the sky. Its energy has spread across a greater distance. Solar panels produce less power. Their surfaces must become larger or more efficient. The spacecraft turns them carefully toward the sun. Every degree of alignment matters more. On Earth, sunlight feels abundant. It reaches forests, oceans, deserts, rooftops, and windows. Beyond Mars, sunlight begins to feel like a resource. It remains powerful enough to operate many systems, yet there is less available energy for each square meter of panel. Power must be managed carefully. Some instruments operate only at scheduled times. Heaters protect delicate components. Batteries store energy for periods when the vehicle turns away from the sun. The crew does not feel this change directly. Cabin lights remain steady. Temperature remains comfortable. Computers continue working. Only the power displays reveal that the spacecraft is entering a dimmer region of the solar system. Outside, the darkness looks unchanged. Space does not become visibly emptier. It has always looked almost empty. Yet the distance between useful destinations is growing. Behind lies Mars. Ahead lies the asteroid belt. Popular images sometimes show this region as a crowded field of rocks. Spacecraft weave between tumbling boulders. Asteroids pass dangerously close. Collisions seem unavoidable. The real asteroid belt is very different. It contains millions of objects, but they are spread across an enormous volume. The average distance between large asteroids is vast. A spacecraft can cross the region without seeing any asteroid closely, unless its path has been designed to approach one. The belt is not a wall. It is a broad collection of separate orbits. Each asteroid follows the sun. Some paths are nearly circular. Others are more stretched. Some objects remain close to the main plane of the planets. Others travel above or below it. They do not move together as one solid band. They are individual worlds sharing a wide region. The crew knows this. Navigation teams have calculated the path precisely. Known objects are tracked. No large asteroid is expected to cross dangerously close. The spacecraft does not need to steer continuously through obstacles. It coasts through emptiness. This is strangely calming. The region often imagined as crowded is mostly distance, yet the emptiness carries its own uncertainty. An asteroid may lie millions of kilometers away and remain invisible to the crew. A camera may detect only a faint point. Without magnification and careful measurement, the object looks no different from a star. Its motion reveals its closeness. Night after night, the point shifts against the distant background. The change is small, but it shows that the object belongs to the solar system rather than the deeper galaxy. The first asteroid discovered was Ceres. Giuseppe Piazzi observed it in 1800. At first, it appeared only as a moving point of light. Later observations revealed that it traveled between Mars and Jupiter. Ceres is now classified as a dwarf planet. It is the largest object in the asteroid belt. Its surface contains bright deposits, dark material, impact craters, and signs that water-rich chemistry has shaped its history. Ceres may contain large amounts of ice beneath its surface. A small world once mistaken for a star may hold more water than its dry appearance suggests. This pattern repeats throughout space. An object looks simple from far away. Closer observation reveals structure. A point becomes a world becomes layers. Rock covers ice, dust hides chemistry. A crater preserves material from below. The farther humanity travels, the more often emptiness becomes detail. The spacecraft does not pass close to Ceres. It crosses another region of the belt. A smaller asteroid lies along the planned route. It has no atmosphere. Its gravity is extremely weak. Its shape is irregular because it does not contain enough mass for gravity to pull it into a sphere. From far away, it resembles a dim star. As the spacecraft approaches, the object slowly gains width. The first images reveal a dark, uneven surface. Crater rims become visible. One side is wider than the other. A ridge crosses part of the body. The asteroid rotates slowly. Sunlight moves across its surface, creating long shadows. There is no air to soften those shadows. The illuminated ground appears pale. The opposite side vanishes into blackness. The asteroid looks divided into existence and absence. One half reflects sunlight. The other half becomes almost invisible. The crew watches through cameras. There is no plan to land. The spacecraft will pass at a safe distance and use instruments to study the object. A spectrometer measures reflected light. Different minerals absorb different wavelengths. The pattern reveals clues about composition. A thermal camera studies heat. A laser altimeter measures shape. Radio tracking reveals how the asteroid's gravity changes the spacecraft's path. From that small change, scientists estimate mass. Mass and volume provide density. Density offers clues about the interior. Some asteroids are solid rock. Others may be fractured collections of pieces held together by weak gravity. These are sometimes called rubble piles. A rubble pile asteroid may contain large empty spaces. Its surface looks stable, yet the interior may resemble a loose mountain of fragments. Collisions in the early solar system broke larger bodies apart. Gravity gathered some pieces again. The object became a new world assembled from the remains of older ones. The astronaut watches the asteroid turn. It is quiet. No dust storm crosses it. No liquid moves. No biological process changes its surface. Yet the object is not inactive. Sunlight warms one side. That heat later radiates away. Tiny temperature differences can alter an asteroid's motion over long periods. Photons carry momentum. When sunlight is absorbed and heat is released in another direction, a very small force appears. This is known as the Yarkovsky effect. The force is almost unimaginably weak, but it acts repeatedly. Over millions of years, it can change an asteroid's orbit. A tiny imbalance in thermal radiation can move a world. Deep space often works this way. Small forces become important because they are given time. A slight gravitational pull changes a spacecraft's path. A weak stream of particles wears at a surface. A small leak becomes serious if it continues. A nearly invisible push moves an asteroid across ages. Time magnifies the quiet. The spacecraft passes the asteroid. Its apparent motion increases as the distance closes. For several hours, it becomes the largest natural object in view. Then it begins shrinking. The encounter ends almost as soon as the asteroid becomes familiar. Images are stored. Measurements are transmitted toward Earth. The radio signal requires many minutes to cross the distance. Scientists receive the data long after the spacecraft has already moved away. The asteroid returns to a point. Eventually, it disappears from the unaided eye. The crew has crossed paths with a small world and left it behind. No rescue station waits there. No fuel depot exists. No sheltered habitat rests beneath the surface. The asteroid contains useful materials, but they remain locked inside rock and metal. Future missions may visit such objects for scientific study. Some asteroids contain water-rich minerals. Others contain iron, nickel, and rarer elements. Their weak gravity could make some mining operations easier than on large planets. But low gravity creates new challenges. A tool pushed against the surface may move the worker backward. Dust may travel slowly and remain suspended on long paths. A spacecraft cannot simply rest on the ground through weight alone. Anchors, harpoons, drills, or carefully controlled thrusters may be required. Landing becomes a form of gentle attachment. The European Space Agency's Rosetta mission demonstrated this difficulty at Comet 67P. Its small lander, Philae, reached the surface in 2014. The anchoring systems did not work as planned. The lander bounced. In the comet's weak gravity, each bounce lasted a long time. Philae eventually settled in a shadowed region. The event showed how unfamiliar movement becomes on a small body. A landing that would end instantly on Earth can continue across hours. Gravity is present. It is simply too weak to behave familiarly. The asteroid belt contains objects from the early solar system. Many have changed less than planets with active geology. They preserve material from the era when the Sun and planets formed. About 4.6 billion years ago, a cloud of gas and dust collapsed. Most material gathered into the Sun. The remainder formed a rotating disk. Dust grains collided and stuck together. Small bodies became larger. Some grew into planets. Others remained as asteroids and comets. Jupiter's immense gravity influenced the region between itself and Mars. Its pull disturbed many growing bodies. Instead of combining into another large planet, much of the material remained separated or was scattered elsewhere. The asteroid belt is therefore not the remains of one exploded planet. It is material that never formed a single full-sized world. The belt is unfinished planetary construction. Every rock is a fragment of possibility. Some asteroids contain metal that once lay inside larger bodies. These parent bodies heated and separated into layers. Heavy metals moved inward. Lighter rock remained near the surface. Later collisions broke those bodies apart. Fragments from their interiors became exposed. A metallic asteroid may therefore contain material that once belonged to the core of an early world. The spacecraft passes through a region filled with pieces of beginnings. This makes the emptiness feel ancient rather than empty. Nothing large is visible nearby, yet the volume contains records of formation, collision, and separation. The solar system's early history remains spread across millions of independent paths. The deeper journey reveals that creation does not always end in completion. Some material becomes a planet, some becomes a moon, some remains as dust, some is scattered into darkness. All continue moving. The crew studies the navigation display. Jupiter remains ahead. It is still far away. The distance from the asteroid belt to the giant planet is enormous. The spacecraft will not cross it quickly. A gravity assist maneuver may be planned. Jupiter's gravity can change the spacecraft's speed and direction relative to the Sun. The vehicle falls toward the planet. Its speed increases. It passes through the moving gravitational field. Then it leaves on a new path. The planet exchanges a tiny amount of orbital energy with the spacecraft. Jupiter's motion changes by an immeasurably small amount. The spacecraft gains or loses far more. This technique has carried probes toward the outer planets. Voyager missions used alignments of giant planets to travel across the solar system. Galileo used gravity assists on the way to Jupiter. Cassini used several planetary encounters before reaching Saturn. A world becomes part of the engine. Gravity performs work without fuel being burned continuously, but a gravity assist requires precision. The spacecraft must approach at the correct time, speed, and angle. Too far away, and the effect is weak. Too close, and radiation, atmosphere, rings, or collision risks may increase. The planet does not adjust itself to meet the spacecraft. The spacecraft must arrive at the proper point in Jupiter's long orbit. Launch windows therefore depend on planetary geometry. A mission may wait years for a useful alignment. Deep space is not crossed through power alone. It is crossed through timing. The crew travels toward a planet that is still only a bright point. Jupiter reflects sunlight strongly. It can be seen from Earth without a telescope. From the spacecraft, it slowly becomes brighter. At first, it resembles a star. Later, a small disk becomes visible through magnification. Its moons appear nearby as points. These moons move from one observation to the next. Their changing positions reveal a miniature planetary system: Io, Europa, Ganymede, Callisto. 4 large moons orbit Jupiter. Galileo Galilei observed them in 1610. Their motion demonstrated that not everything circles Earth. The discovery helped change humanity's understanding of its place in the universe. Now the spacecraft approaches the same system from outside. What once appeared as points in a telescope become destinations. Europa may contain a global ocean beneath ice. Ganymede is larger than Mercury and possesses its own magnetic field. Io is shaped by intense tides and active volcanism. Callisto preserves an ancient cratered surface. Jupiter is not only a planet, it is the center of a complex family. Yet reaching it means entering a harsher environment. Jupiter's magnetic field is enormous. It traps charged particles and creates powerful radiation belts. A spacecraft passing near the planet must protect electronics carefully. Some orbits are chosen to reduce exposure. Components may be placed inside shielded vaults. Mission duration near intense regions may be limited. Jupiter's beauty and severity come from the same immense scale. Its rapid rotation, internal heat, magnetic field, and moons create a dynamic environment. The planet does not need to threaten a spacecraft deliberately. Its ordinary physics is enough. The astronaut studies the route. The vehicle remains far from Jupiter's strongest radiation. For now, the main challenge is distance. Messages from Earth take longer to arrive. The crew sends a technical question. The signal travels toward the inner solar system. It passes Mars's orbit. It continues toward Earth. Mission Control receives it much later. Engineers analyze the problem. A response begins the return journey. By the time the crew hears the answer, hours may have passed. This changes how emergencies must be managed. Earth can offer knowledge. It cannot provide immediate control. The spacecraft must contain enough expertise to respond locally. Crew members train across several fields. A pilot may understand medical procedures. A scientist may learn electrical repair. A doctor may assist with navigation systems. No one can remain limited to one narrow role. Deep space rewards flexibility. The crew becomes a small community of overlapping knowledge. Artificial intelligence and onboard software may provide additional support. A diagnostic system can compare symptoms with stored information. A maintenance program can guide repair. A navigation computer can evaluate alternatives. But software also depends on power, sensors, and correct data. It assists judgment. It does not remove responsibility. The crew still observes, questions, tests, decides. The farther Earth recedes, the more the mission becomes its own center of action. During one sleep period, a small alarm sounds. It is not a major emergency. A temperature sensor reports that an equipment compartment is warmer than expected. The crew wakes. A camera checks the area. A fan is not operating at full speed. Airflow has decreased. Heat from electronics is gathering. A replacement fan is available. The system has redundancy. The crew follows the procedure. Power is reduced to the affected equipment. A panel is opened. The fan assembly is removed. A small piece of debris has entered the intake. It may be a fragment of packaging or fabric. In microgravity, the particle did not fall to a floor. Airflow carried it toward the fan. The obstruction is removed. The fan begins operating normally. Temperature returns to the expected range. The event lasts less than an hour. On Earth, it would be a minor maintenance problem. Beyond Mars, it feels more significant. No technician can visit. No new fan can arrive. The crew and its stored supplies are the entire repair system. Yet the problem is solved calmly. Deep space has not made the crew helpless. It has made preparation visible. The station's equipment works because someone planned for a fan to fail. A spare exists. Tools fit the assembly. Instructions are available. Training turns distance into independence. After the repair, the astronaut returns to the window. Nothing outside has changed. The sun remains small and bright. Jupiter remains ahead. The asteroid belt surrounds the route with objects too distant to see. The spacecraft's reflection appears faintly in the glass. The face looks tired but calm. Behind it are stars. For a moment, the reflection seems to float outside. The illusion is familiar. It no longer suggests a visitor. It simply shows a human face layered over the solar system. The deeper journey has become more severe. Power is less abundant. Communication is slower. Destinations are farther apart. Radiation environments grow more complex. A small mechanical problem carries greater weight. Yet none of these conditions needs to become horror. They are measurable. They can be studied. Some can be designed around. Others can be accepted as limits. The crew closes the equipment panel. The cabin returns to its ordinary hum. The fan that briefly stopped now becomes part of the familiar background again. Outside, the asteroid belt continues moving around the sun. Millions of bodies follow separate paths through a region too wide to appear crowded. The astronaut prepares for sleep. Mars glows behind as a small reddish point. Jupiter shines ahead. Between them lies a distance containing ancient fragments, invisible forces, and almost no shelter. The spacecraft carries its own air, its own warmth, its own measured light. The deeper it travels, the less the universe offers freely, but the more clearly every working system becomes an act of quiet human foresight. Jupiter grows slowly. For weeks it remains a bright point ahead of the spacecraft. It looks almost like a star, except that its position changes slightly against the distant background. Then the point becomes a disk. Bands appear across its atmosphere. Pale regions alternate with darker belts. Enormous weather systems turn within them. The planet rotates once in less than 10 Earth hours, making it the fastest spinning planet in the solar system. Its rapid rotation stretches the world slightly around the equator. Jupiter is not a perfect sphere. It is wider through its middle. The spacecraft approaches carefully. Jupiter contains more mass than all the other planets combined. Its gravity influences asteroids, comets, moons, and spacecraft across a wide region. Yet the crew does not feel the planet pulling directly. Inside the cabin, bodies remain weightless. A loose strap continues floating. A small droplet remains inside its container. Only the navigation display reveals that the spacecraft's speed is increasing. It is falling toward Jupiter. The word falling sounds dramatic, but orbital motion is a controlled form of falling. The spacecraft follows a calculated path through the planet's gravitational field. Its engines do not need to push continuously. Gravity provides much of the acceleration. Jupiter becomes part of the journey. The deeper the vehicle falls toward the planet, the faster it moves. If the path is correct, the spacecraft will curve around Jupiter and depart in a new direction. The maneuver can increase its speed relative to the Sun. A world millions of times more massive than the spacecraft lends a tiny fraction of its orbital momentum. Jupiter does not notice the exchange. For the vehicle, the effect may shorten years of travel. This is the quiet usefulness of gravity. It pulls without machinery. It guides without sound. It connects the movement of small spacecraft to the motion of entire planets. As Jupiter grows larger, its atmosphere becomes more detailed. The planet has no solid surface where a spacecraft could land in the usual sense. Its visible clouds form only the upper layers of an immense atmosphere. Deeper down, pressure and temperature rise. Hydrogen changes under those conditions. It becomes compressed. Far below the clouds, it may behave like a liquid. Deeper still, pressure turns hydrogen into a metallic state that conducts electricity. Movement within this electrically conducting material helps generate Jupiter's powerful magnetic field. The planet is a world of increasing pressure. A descending probe would encounter thicker gas, stronger compression, and greater heat. There is no clear ground waiting below. Eventually, the environment becomes too severe for ordinary spacecraft. The Galileo mission released an atmospheric probe into Jupiter in The probe entered at great speed. A heat shield protected it during the first intense moments. It then descended beneath a parachute, measuring temperature, pressure, winds, and composition. The probe transmitted information for less than an hour before increasing pressure and temperature ended its operation. It did not reach a surface. It entered a planet whose atmosphere gradually became an interior. The astronaut watches Jupiter through magnified cameras. The great red spot is visible. It is an enormous storm that has persisted for centuries, though its size and shape continue changing. Winds circle the system. Clouds rise and sink. Chemical compounds create its colors. The storm is larger than Earth, yet from the spacecraft it appears as one oval within a much larger world. Scale changes meaning again. A storm capable of covering a planet becomes one detail on Jupiter. Smaller white ovals turn nearby. Long bands flow in opposite directions. Turbulence forms curls and folded structures between them. The atmosphere resembles paint moving through water, but the actual system extends across thousands of kilometers. There is no quiet surface beneath these clouds. The motion continues downward. Jupiter releases more heat than it receives from the Sun. Energy left from its formation still escapes from within. The planet is slowly cooling. Gravity compresses its interior. Heat rises and helps drive atmospheric movement. Jupiter is not simply reflecting sunlight. It carries an internal glow too faint for human eyes, but measurable in infrared light. The spacecraft remains far above the clouds. It will not enter the atmosphere. The greater concern lies in the invisible regions surrounding the planet. Jupiter's magnetic field is enormous. It creates the largest planetary magnetosphere in the solar system. On the side facing the Sun, the magnetic environment extends millions of kilometers. On the night side, it stretches into a long tail that may reach beyond Saturn's orbit. The magnetosphere traps charged particles. These particles move along magnetic field lines and form intense radiation belts. Near some regions, the environment is much stronger than the radiation belts around Earth. Electronics can be damaged. Detectors can become overwhelmed. Materials can slowly change. A crewed spacecraft would need careful shielding and a route that limits exposure. The approach has been planned for this reason. The vehicle does not pass through the most intense inner region. Its path remains farther away, using Jupiter's gravity while avoiding unnecessary radiation. Distance from the planet is not chosen only for navigation. It is chosen for survival. The radiation monitors begin showing an increase. The change is expected. Crew members check the readings. The spacecraft's most sensitive electronics are protected within shielded compartments. Critical systems use redundancy and error correction. The crew's sleeping and working areas lie behind water, supplies, and structural material. No special shelter is required yet. Still, the numbers rise. Jupiter's magnetic environment is becoming real through instruments. Outside the window, nothing announces it. The stars remain visible. The atmosphere of Jupiter turns below. No glowing wall surrounds the planet. No visible particles strike the hull. Only graphs and detector counts reveal that the spacecraft has entered a different region. The astronaut remembers the solar storm. Once again, the senses remain calm while instruments describe a more energetic universe. This dependence on measurement has become familiar. Deep space does not always hide danger deliberately. It simply contains conditions human bodies never evolved to notice. The spacecraft passes one of Jupiter's outer moons. The moon appears small at first, then craters become visible. It is Callisto. Callisto is one of the most heavily cratered worlds in the solar system. Its surface has changed relatively little compared with more active moons. There are no great mountain chains created by recent plate movement. No widespread volcanic plains renew the landscape. Ancient impacts overlap across ice and rock. Callisto lies farther from Jupiter than the other large Galilean moons. Its radiation environment is milder than the regions closer to the planet. For this reason, some mission studies have considered it a possible location for future human operations in the Jovian system. Even there, the challenges would be immense. Sunlight is weaker, communication with Earth is slow, the surface offers no breathable air, temperatures remain extremely low. Yet compared with Jupiter's inner moons, Callisto occupies a quieter region. The spacecraft does not land. It passes at a great distance. The moon shrinks behind. Ahead lies Ganymede. Ganymede is the largest moon in the solar system. It is larger than the planet Mercury, though it contains less mass. Its surface shows both old dark terrain and younger, brighter regions cut by grooves and ridges. Beneath its ice may lie a deep ocean. Ganymede is also the only moon known to generate its own intrinsic magnetic field. A small magnetosphere exists within Jupiter's much larger one. One magnetic world moves inside another. Particles respond to both fields. Auroras appear near Ganymede's poles. Their motion has helped scientists infer the presence of a salty ocean beneath the surface. The ocean may contain more water than all the oceans on Earth, but it lies beneath an enormous thickness of ice. Water can be abundant and still inaccessible. A future mission would need to cross frozen layers, survive radiation, and operate far from Earth. The presence of water alone does not make a world easy to explore. It simply makes the world more interesting. The spacecraft's cameras turn toward Europa. Europa appears bright and smooth compared with Callisto. Long dark lines cross its icy shell. Some form double ridges. Others create wide bands where the surface may have opened and refrozen. There are relatively few large impact craters. This suggests that Europa's surface is geologically young. Something has erased older scars. The leading explanation is movement within the ice, powered partly by tidal forces from Jupiter and neighboring moons. Europa does not travel in a perfectly circular orbit. Its distance from Jupiter changes slightly. The planet's gravity stretches the moon by different amounts during each orbit. This repeated flexing produces heat. Beneath the frozen exterior, a global ocean may remain liquid. The water is hidden from sunlight. It may touch a rocky seafloor. Chemical reactions there could provide energy. On Earth, ecosystems exist near hydrothermal vents without depending directly on sunlight. Microorganisms use chemical energy released by interactions between water and rock. This does not prove life exists in Europa's ocean. It shows why the moon receives so much scientific attention. A world can remain frozen outside while carrying liquid movement below. The calm white surface may hide an active interior. Europa also lies within a powerful radiation environment. Charged particles strike its surface continuously. They alter the ice and create chemical compounds. Some of those compounds may eventually move downward through cracks or recycling ice, possibly carrying useful chemistry into the ocean. Radiation that is harmful at the surface may help create ingredients relevant to life below. The same process can be obstacle and opportunity. The universe rarely divides itself into simple categories. A harsh environment may produce useful chemistry. A protective ice shell may also make exploration difficult. A moon that seems quiet may be active beneath kilometers of frozen water. The spacecraft passes far enough away to protect the crew. Even from this distance, Europa becomes one of the most meaningful objects in the journey. The astronaut looks at its bright disk. No ocean is visible. No movement can be seen beneath the ice. There is only a pale world marked by long lines. Evidence for the ocean comes from gravity, magnetic measurements, geology, and physical models. Again, instruments reveal a reality hidden from the eyes. The next moon is Io. Io appears yellow, orange, white, and red. Its surface is covered with sulfur compounds and volcanic deposits. It is the most volcanically active world known in the solar system. Jupiter's gravity stretches Io powerfully. The neighboring moons help maintain the slightly non-circular orbit that keeps this flexing active. The moon's interior heats. Volcanoes release material hundreds of kilometers above the surface. Some plumes rise so high that spacecraft can photograph them against space. Io's landscape changes continually. Lava flows spread. Volcanic deposits cover older terrain. Large mountains rise from the crust. There are few impact craters because volcanic activity erases them. The moon looks alive with movement, though no biological life has been found there. Its activity is geological. Jupiter's gravity supplies the rhythm. The same planet that accelerates the spacecraft also needs the interior of a moon. Gravity shapes motion at every scale. It curves the spacecraft's path. It stretches Io. It warms Europa. It holds Jupiter's atmosphere together. It organizes dozens of moons. The astronaut begins to see Jupiter, not as one object, but as a system. The giant planet sits at the center. Moons travel around it. Magnetic fields guide particles. Volcanoes release material. Dust forms faint rings. Auroras glow near the poles. Every part influences another. Deep space is not empty around Jupiter. It is structured by gravity and magnetism. Yet the system remains widely separated. The spacecraft can pass between moons without seeing another object nearby. Scale still dominates. The crew prepares for the closest part of the planned encounter. Navigation data is reviewed. Communication with Earth carries a long delay. The ground team cannot react immediately. Commands were prepared earlier. The crew monitors the vehicle locally. Jupiter fills a large region of the window. Its clouds move almost imperceptibly at this scale. Though their winds are powerful, the spacecraft's speed increases. There is no sensation of rushing. No air presses against the hull. The cabin remains calm. A tone confirms that the vehicle has reached a planned point. The spacecraft begins curving around Jupiter. Behind the scenes, gravity is changing its direction. The crew watches the trajectory display. A predicted line bends near the planet and extends outward on a new course. The maneuver is working. Jupiter's great mass is reshaping the mission. The astronaut looks toward the planet one last time. The great red spot moves toward the edge. Bands curve around the sphere. A moon casts a small shadow onto the clouds. The shadow looks like a dark dot. It is the silhouette of a world crossing sunlight. From Jupiter's atmosphere, that moon would produce an eclipse. Even a giant planet experiences temporary darkness created by something smaller. The spacecraft moves away. Jupiter begins shrinking. The radiation readings gradually decline. The magnetosphere releases the vehicle slowly, not through a visible boundary, but through decreasing particle counts. The spacecraft has gained speed. Its new path extends toward the outer solar system. The encounter that took years to reach begins becoming memory. One by one, the moons return to points. Jupiter's cloud bands lose detail. The planet becomes a bright disk. Eventually it will look like a star again. The astronaut feels the familiar mixture of relief and distance. A powerful environment has been crossed successfully. Nothing struck the spacecraft. No system failed. The most intense forces remained invisible and measurable. Jupiter seemed severe because of its radiation, gravity, pressure, and storms. Yet each condition followed physical rules. There was no intention behind them. The planet did not pull the spacecraft closer out of curiosity. Its radiation did not search for the crew. Its storms did not notice the passing vehicle. The universe can be difficult without being watchful. This distinction has become important. Fear often imagines a mind behind danger. Science reveals processes: gravity, pressure, magnetism, heat, motion. These can be powerful enough to shape worlds, yet they carry no desire. The spacecraft continues outward. Jupiter fades behind it. Ahead lies a region where sunlight is weaker, communication slower, and planets farther apart. The cabin lights remain unchanged. Air continues moving. The crew prepares new schedules. Data from the encounter is stored and transmitted toward Earth. It will take time to arrive. Scientists will study the measurements long after the spacecraft has left Jupiter behind. The astronaut enters the sleeping compartment. A faint vibration travels through the structure as a small course correction ends. Then the familiar hum returns. Outside, Jupiter continues rotating. Io continues erupting. Europa's hidden ocean continues moving beneath ice. Ganymede carries its magnetic field. Callisto preserves ancient impacts. The system does not pause because a spacecraft has passed. It continues through its own deep time. The astronaut closes the eyes. The journey has entered a colder and wider region. Jupiter has shown that the farther one travels, the larger natural forces can become. But it has also shown that even a giant planet can be understood one measurement at a time. And behind the quiet walls of the spacecraft, understanding remains its own form of shelter. Saturn first appears as a pale point. From Earth, it can be seen without a telescope. It looks like a steady star, moving slowly across the night over months and years. Through a telescope, the planet becomes unmistakable. A small golden sphere sits inside a thin ring, but from the approaching spacecraft, that familiar image changes gradually. The point becomes a disk. The ring widens. Dark gaps appear within it. Moons begin separating from the background stars. Saturn becomes not one object, but a vast arrangement of moving material. The planet is less massive than Jupiter, yet still enormous. More than 700 Earths could fit inside its volume. Its average density is lower than that of water, though no ocean could ever hold a planet. Like Jupiter, Saturn is made mostly of hydrogen and helium. There is no ordinary solid surface beneath its visible clouds. Pressure increases with depth. Gas becomes compressed. Hydrogen changes into fluid and metallic states. Far below the atmosphere, a dense core may contain rock, ice, and heavier material. The spacecraft will not descend. It remains outside, where sunlight reveals the planet's pale bands. Saturn's atmosphere appears calmer than Jupiter's from a distance. Its colors are softer, cream, gold, gray. But powerful winds move within those muted clouds. Near the equator, they can travel faster than sound moves through Earth's atmosphere. Large storms occasionally appear. One immense storm may spread around much of the planet before fading. At the North Pole, a six-sided jet stream forms a structure known as the hexagon. It is wider than Earth. Winds follow the edges of the shape as Saturn rotates beneath them. The hexagon has persisted for decades of observation. Its exact stability remains a subject of study. A geometric pattern exists inside moving gas. The atmosphere produces order without walls. Saturn rotates quickly. One day lasts only about 10.5 Earth hours. This rapid rotation flattens the planet at its poles and widens it around the equator. The rings follow the same broad plane. As the spacecraft approaches, the rings seem almost solid. Sunlight reflects from them brightly. Yet they are not a single surface. They are made of countless individual particles. Most are water ice. Some contain dust and rock. Their sizes range from tiny grains to objects as large as buildings. Each piece follows its own orbit around Saturn. Together they create broad, luminous bands. The spaces between particles are enormous compared with their sizes. A spacecraft can cross the ring plane through carefully selected gaps, but approaching the main rings directly would expose it to many possible impacts. Navigation teams therefore treat the system with precision. Saturn's rings stretch hundreds of thousands of kilometers across, yet in many places, their thickness is measured in only tens of meters. A structure wider than planets can be thinner than a tall building. From far away, the rings seem substantial. From the side, they can nearly disappear. Their beauty depends on viewpoint. When sunlight strikes from the correct angle, icy particles brighten. When seen edge-on, the vast system becomes a narrow line. This is another lesson of deep space. Appearance changes with geometry. A ring becomes a line. A world becomes a point. A nearby particle becomes a streak. A reflection becomes a shape. Understanding begins by asking where the light comes from and where the observer is located. The astronaut watches shadows move across the rings. Saturn casts a wide darkness behind itself. The shadow stretches over the icy bands, creating a long wedge where sunlight cannot reach. On the opposite side, the rings cast thin shadows onto the planet's clouds. The shadows curve with the bands. The planet and rings draw one another in darkness. There is no sound. Billions of particles move around Saturn. Some collide gently. Some break apart. Some gather temporarily into clumps before tidal forces separate them again. Small moons create waves and gaps. Their gravity pushes nearby particles. Ring edges become rippled. Narrow structures form. Everything is moving, yet the system appears perfectly still from a distance. The astronaut understands that stillness in space is often an illusion created by scale. A moon may travel thousands of kilometers while seeming fixed beside the planet. A ring particle may complete an orbit while the human eye notices nothing. The universe does not need to move slowly. It only needs to be large. The spacecraft remains outside the densest rings. Its path brings it near Titan. Titan is Saturn's largest moon. It is larger than the planet Mercury. A thick atmosphere surrounds it, hiding the surface beneath orange haze. Titan is the only moon in the solar system with a dense atmosphere. Nitrogen forms most of it. Methane and other compounds contribute to complex chemistry. From orbit, the moon looks soft and featureless. The haze prevents ordinary visible light from reaching the ground clearly. Radar and infrared instruments are needed to see beneath it. The first radar maps revealed landscapes, mountains, dunes, river channels, lakes, seas. But Titan's lakes are not filled with water. They contain liquid methane and ethane. At Titan's low temperatures, these substances behave somewhat like water does on Earth. They evaporate, form clouds, fall as rain, flow through channels, collect in basins. Titan has weather. It has a cycle of liquid and atmosphere, yet the chemistry is unfamiliar. Water exists there mainly as frozen rock. The surface ice is so cold and hard that it forms the ground itself. Methane moves above it. A person standing on Titan would experience weak gravity and thick air. With suitable equipment, human-powered flight might be possible because the atmosphere is dense and gravity is low. But the cold would be extreme. The air would not be breathable. The sunlight would be dim. Saturn would remain hidden behind haze much of the time. Titan is strangely Earth-like and completely alien at once. It has rivers without liquid water, rain without warmth, seas beneath an orange sky. The spacecraft receives data from instruments designed to examine the moon. Radar pulses travel downward. They pass through the haze. They reflect from the surface. The returning signals create maps. Dark, smooth regions suggest liquid. Rougher areas reflect more strongly. A shoreline appears. The crew cannot see it directly. The landscape is reconstructed from radio echoes. Deep space repeatedly removes the easy view. Some worlds hide beneath ice. Others hide beneath clouds. Others hide beneath darkness. Human senses reach only the surface of observation. Technology translates what cannot be seen. Titan also contains organic molecules. Sunlight and energetic particles interact with methane and nitrogen high in the atmosphere. They create more complicated carbon-based compounds. These gather into haze and fall toward the surface. Over long periods, Titan may accumulate a rich inventory of organic chemistry. Organic does not necessarily mean biological. It refers to compounds containing carbon, often combined with hydrogen and other elements. Life on Earth depends on organic chemistry, but organic molecules can form without life. Titan is valuable because it shows how far chemistry can progress in a cold environment. Its surface may resemble certain aspects of the early Earth, though temperatures and materials are very different. Beneath Titan's icy crust, another ocean may exist. Liquid water mixed with salts could remain hidden deep below. The outer solar system contains water in places where no blue ocean can be seen. It is buried, frozen, covered by rock or atmosphere. The farther humanity travels, the more familiar substances appear in unfamiliar forms. Water becomes stone, methane becomes rain, hydrogen becomes metal. The universe rearranges ordinary elements through pressure and temperature. The spacecraft continues through Saturn's system. Enceladus comes into view. It is much smaller than Titan. Its surface is bright because it is covered in clean water ice. Long cracks cross the south polar region. From these fractures, jets of vapor and icy grains rise into space. The material comes from a hidden ocean beneath the crust. Some of the particles escape and help form Saturn's E-ring. A moon only a few hundred kilometers wide contributes material to a ring surrounding a giant planet. Spacecraft have flown through the plumes. They detected water vapor, salts, silica particles, and organic compounds. The silica may form through interactions between warm water and rock near the moon's seafloor. This suggests hydrothermal activity. On Earth, hydrothermal environments support ecosystems. Again, this does not prove life exists on Enceladus. It shows that several ingredients and energy sources may be present. The moon offers a rare opportunity. Its hidden ocean sends samples into space naturally. A future spacecraft may collect material without drilling through kilometers of ice. The astronaut watches a magnified image of the plumes. They appear as delicate white streams rising from the moon's edge. The jets move silently into vacuum. Small particles catch sunlight. Some fall back. Others spread around Saturn. A world releases part of its ocean grain by grain. The sight is calm, yet it changes the meaning of the outer solar system. Far from the sun, where warmth is weak, liquid water can still exist. Tidal gravity provides energy. Rock and water interact. Chemistry continues beneath ice. The deeper journey is not moving toward complete stillness. It is moving toward hidden activity. The surface may freeze. The interior may remain alive with heat and motion. Saturn begins receding. Its rings narrow. The system that filled the windows slowly becomes a bright oval. The spacecraft continues outward. Ahead lies Uranus. The journey between planets lengthens again. Saturn and Uranus are separated by more than 1 billion kilometers. Nothing large lies directly along most of the path. The sun grows smaller. Its light is still far brighter than every other star. But its warmth has weakened greatly. Solar panels become increasingly difficult to use. A crewed spacecraft traveling this far would probably depend on nuclear power. Radioisotope systems produce electricity from the heat released by radioactive decay. The process is steady. It does not depend on sunlight. For decades, such systems have powered probes across the outer solar system. They operate quietly. Heat flows through special materials. Part of it becomes electricity. The rest must be released. Power decreases slowly as the radioactive material decays and components age. Every instrument competes for energy. Some are switched off during long cruise periods. Heaters protect essential systems. The spacecraft sleeps partially between encounters. A crewed mission could not reduce activity so deeply. Humans require continuous life support. Air must circulate. Water must be processed. Temperature must remain stable. Food must be stored safely. Medical systems must remain ready. The farther a crew travels, the more power becomes a question of endurance. A brief interruption near Earth may be manageable. Far beyond Saturn, reliable energy must continue for years. The mission clock becomes as important as distance. The journey to the outer planets is not only far, it is long. The crew watches Earth's messages arrive after hours. A reply takes the same time to return. One exchange may require most of a day. Mission Control sends a question. The crew answers. Earth receives the answer much later. By then, the crew may already be sleeping. Conversation has become a sequence of separated days. The astronaut records a message for home. There is no expectation of an immediate response. The words are chosen slowly. A view of Saturn is described. Titan's haze, Enceladus's plumes. The pale rings fading behind the spacecraft. The message includes ordinary details too. A meal, a repair, a joke shared during exercise. The extraordinary and ordinary remain close together. Deep space does not remove daily life. It carries it farther. The spacecraft approaches Uranus. The planet appears blue-green because methane in its atmosphere absorbs red light. Its visible surface looks unusually smooth. Faint bands and storms exist, but they can be difficult to see. Uranus rotates on its side. Its axis is tilted by about 98 degrees. Most planets spin with their poles roughly above and below their orbital planes. Uranus appears to roll around the Sun. The cause is uncertain. A large collision early in its history may have changed its orientation. Another possibility involves a series of gravitational interactions. Whatever happened, the effect remains billions of years later. Each pole can experience decades of sunlight, followed by decades of darkness. Seasons become extreme in duration. The planet's magnetic field is also tilted strongly and offset from its center. As Uranus rotates, the magnetic environment moves in a complicated way around it. A world can be quiet in appearance and unusual in structure. Its rings are dark and narrow. Its moons contain ice and rock. Some show signs of fractures and past geological activity. The spacecraft does not remain long. There is no human base, no orbiting laboratory, no vehicle waiting to refuel it. Every world encountered is scientifically rich and practically empty. This separation becomes more noticeable with distance. Near Earth, space is filled with human signals. Satellites broadcast. Stations orbit. Radar tracks objects. The Moon receives growing attention. Near Uranus, human presence is represented by only a few distant probes and old transmissions. The planet has been visited closely by one spacecraft, Voyager 2, during a brief flyby in night. Most knowledge comes from that encounter and telescopic observation. A giant world remains largely unexplored. The spacecraft turns toward Neptune. The Sun is now more than 4 billion kilometers away. Sunlight takes over 4 hours to reach this region. A message sent to Earth must cross the same distance. Every image is old before anyone receives it. The planet visible through the window is being seen as it was hours earlier. Earth sees the spacecraft in the past. The spacecraft sees Earth in the past. There is no shared present across such distance. Relativity does not provide one universal moment that all observers experience identically. But even without entering deeper theory, communication delay creates a practical truth. Remote worlds cannot speak instantly. Every exchange crosses time as well as space. Neptune appears deep blue. Methane contributes to its color, though other atmospheric processes may also affect the shade. The planet receives far less sunlight than Earth, yet it has some of the fastest winds in the solar system. Dark storm systems form and disappear. Bright clouds of frozen methane move above them. Neptune releases more internal heat than it receives from the Sun. That heat helps drive its atmosphere. The outer solar system is not simply becoming colder and quieter. Internal energy continues shaping worlds. Triton, Neptune's largest moon, orbits in the opposite direction from most large moons. This suggests it was captured. It may once have been an independent object, traveling around the Sun. Neptune's gravity brought it into orbit. The capture likely disturbed the planet's original moon system. Some moons may have collided. Others may have been ejected. Triton's orbit gradually changes. Far in the future, it may move close enough to be torn apart by tidal forces, perhaps forming new rings around Neptune. A moon can become a ring. A ring can gather into moons. The solar system is not a finished museum. It continues evolving. The spacecraft passes Neptune. The blue disk shrinks. The last major planet falls behind. Ahead lies the Kuiper Belt. Pluto and many other icy worlds move there. Beyond them, the solar system extends farther through scattered objects and a distant possible cloud of comets. There is no clear wall. No sign marks the end of the planets. Human language divides regions for understanding. Nature changes gradually. The astronaut looks back. The sun appears bright but small. It no longer dominates the view in the way it did near Earth. From this distance, it begins to resemble a very brilliant star. Its warmth outside the spacecraft is weak. The planet of origin cannot be seen without instruments. Earth has become hidden inside the sun's glare from some angles or lost among stars from others. Home is no longer a visible world. It is a direction, a set of coordinates, a memory carried inside light-delayed messages. This may be the deepest change so far. Earlier in the journey, Earth grew smaller. Now it has become visually absent. The astronaut cannot look through a window and identify it easily. Navigation systems know where it is. Antennas point toward it. Signals arrive from it. But the eye alone no longer finds home. The spacecraft becomes the only immediate place. Its walls contain all breathable air. Its lights create the local day. Its clocks define waking and sleep. Its records hold voices from Earth. Its windows open onto a solar system in which no nearby object belongs to humanity. The deeper journey has not revealed creatures waiting among the planets. It has revealed how quickly human life becomes dependent on what it carries. Protection no longer comes from Earth's atmosphere. Energy no longer arrives abundantly from the sun. Communication no longer resembles conversation. Resupply no longer exists. Every useful condition must be maintained locally. Yet the crew continues. Air circulates. Water returns through filters. Food is counted. Exercise preserves the body. Messages preserve connection. Science gives meaning to distance. The astronaut enters the sleeping compartment. The body is secured gently. Outside, Neptune continues shrinking. The sun shines from farther away. No large world fills the sky. The spacecraft is moving toward the region where the solar wind itself will weaken. Beyond waits the boundary between the sun's extended atmosphere and the material between stars. It will not look like a gate. It will not appear as a line of light. Only instruments will know when the crossing begins. The astronaut closes the eyes. Saturn's rings are now far behind. Uranus and Neptune have returned to points. Sunlight has faded, but it has not disappeared. The spacecraft carries warmth through its own quiet systems, and while the universe outside grows colder and wider, the small human world inside continues shining with the measured steadiness of something designed to endure. The sun does not end at Neptune. Its visible disk has become small. Its warmth has weakened. Its planets now lie behind the spacecraft, yet the star still surrounds the journey in another form. The solar wind continues flowing outward. It carries charged particles away from the sun in every direction. Near Earth, this stream moves rapidly through space. Farther away, it expands and becomes thinner. It passes Mars, Jupiter, Saturn, Uranus, Neptune. It continues into the darkness beyond the known planets. The spacecraft travels within this enormous region. Scientists call it the heliosphere. It is a vast bubble created by the sun's particles and magnetic field. Every planet moves inside it. Every asteroid and comet in the inner solar system moves inside it. The heliosphere is not perfectly round. The sun itself travels through the Milky Way. Material between the stars presses against the solar wind. Magnetic fields influence the boundary. The resulting shape may be stretched, uneven, and constantly changing. Humanity cannot photograph the entire heliosphere from the outside. It is too large. The solar system lies within it. Understanding comes from measurements made in different locations. Spacecraft detect particle speeds, magnetic fields, radiation, plasma density. Each instrument observes only the surrounding region. Together, the observations reveal the shape of an invisible structure. The sun has carried part of itself far beyond the planets. Its light reaches much farther, but its material influence eventually begins to weaken. The solar wind slows. Pressure from the interstellar medium becomes more important. The spacecraft approaches a region called the termination shock. The name sounds sudden. The crossing is not visible. No wave appears outside the window. No wall waits ahead. The termination shock is where the outward-moving solar wind slows sharply because it begins pressing against material between the stars. Particles that once moved faster than the local speed of disturbances within the plasma become slower. Their temperature and density change. Magnetic conditions change as well. A detector notices first. The flow of charged particles shifts. The distribution of energy becomes different. The spacecraft has crossed a boundary that the eye cannot see. Inside the cabin, nothing moves. Air continues circulating. Lights remain steady. The crew feels no impact. One environment has quietly become another. This pattern has followed the journey from the beginning. Earth's atmosphere faded gradually. The magnetosphere had invisible borders. Radiation belts were crossed without visible signs. The solar wind carried storms that produced no sound. Now the sun's outer region changes through measurements alone. The deeper the spacecraft travels, the more important invisible boundaries become. A coastline can be seen. A mountain range can be mapped by sight. The edge of a magnetic environment must be inferred. Nature contains borders that are not surfaces. They are changes in behavior. A particle moves differently. A field turns. A density rises. A signal becomes weaker. Science gives names to these transitions so that they can be followed. Beyond the termination shock lies the heliosheath. The solar wind continues moving there, but more slowly. It becomes compressed and disturbed. The region is not calm in a simple sense. Magnetic fields twist. Particles from different sources interact. Some solar material turns and flows along the outer boundary. The spacecraft moves through this region for a long time. Distances are still enormous. Crossing one boundary does not mean the next lies nearby. Voyager 1 passed the termination shock in 2004. It did not cross into interstellar space until 2012. Voyager 2 reached the same major transitions at different distances and times. This difference showed that the heliosphere changes. Solar activity influences its size. The pressure outside varies. The boundary moves inward and outward. The sun's outer shelter breathes slowly across years. The astronaut studies data from those earlier robotic missions. They traveled this route without people on board. Their instruments continued working long after their original planetary encounters. Voyager 1 and Voyager 2 were launched in 1977. Then they continued outward. Decades passed. Their power weakened gradually. Some instruments were turned off to preserve energy. Signals grew fainter, yet the spacecraft remained connected to Earth. Large radio antennas listened for transmissions, carrying very little power across billions of kilometers. A signal from Voyager may reach Earth with less power than the energy produced by a small household light. Sensitive receivers collect it. Computers separate information from background noise. A machine built during one human generation speaks to another from the edge of the sun's influence. The astronaut finds comfort in this. Distance does not always end communication. It changes the scale of listening. A strong signal is no longer expected. Patience and precision become more important. An antenna must point correctly. Receivers must know where and when to listen. Noise must be studied rather than ignored. Deep space communication is an act of careful attention. The crew's own signal takes many hours to reach Earth now. A message is sent. The spacecraft continues traveling. The crew eats, works, exercises, sleeps. Only later does Earth receive the transmission. A response begins its return journey. By the time it arrives, the original message may belong to the previous day. Urgent conversation is impossible. The spacecraft has become largely independent. Mission control can still provide long-term guidance. Engineers can study complicated problems. Scientists can suggest observations. Families can send recorded words. But every immediate decision belongs to the crew. This independence has developed gradually. Near Earth, help was seconds away through radio. Behind the Moon, silence lasted only minutes. Near Mars, delay interrupted conversation. Beyond Neptune, Earth and spacecraft no longer share the same working moment. Each side continues separately, while messages cross between them. The crew begins treating communication like a river. Information flows in both directions, but no one can step into the same water at the same time. Questions leave, answers return later. The connection remains real. It simply cannot hurry. Outside, the stars appear unchanged. The nearest stars are still many light years away. A light year is the distance light travels in 1 year. Light moves nearly 300,000 kilometers each second. Even at that speed, the nearest star system beyond the Sun requires more than 4 years to reach Earth. A spacecraft moving at present human speeds would require thousands of years to cross the same distance. This is where the scale of interstellar space becomes clear. The outer solar system felt immense. Interstellar distance is much greater. If the distance from the Sun to Neptune were represented by a single step, the nearest star would still be many thousands of steps away. The planets occupy one small neighborhood. The next neighborhood lies across a wide and nearly empty region. The astronaut looks toward Alpha Centauri. The system appears as a bright point from the spacecraft's location. Its individual stars may require magnification and careful instruments to separate. One member, Proxima Centauri, is the nearest known star to the Sun. It is a small red dwarf. A planet orbits within a region where temperatures might allow liquid water under suitable conditions, but the star produces strong flares. Its planet may receive intense radiation. An atmosphere, magnetic field, oceans, geology, and many other factors would determine whether the surface could support familiar life. From this distance, none of that can be seen directly. The star remains light. The planet remains hidden inside its glare. A whole possible world exists as a pattern within data. The deeper journey has not brought the crew close to another star. It has only revealed how far away every star truly is. On Earth, the night sky feels crowded. Thousands of points may be visible under dark conditions. They appear painted across one surface, but they are spread through three-dimensional space. Some are tens of light years away, others hundreds. Some visible objects lie thousands or millions of light years away. The eye compresses these distances into a single dark dome. Space travel begins unfolding the dome into depth. One star is relatively near, another lies far behind it. A faint patch may be an entire galaxy. Brightness does not always indicate distance. A powerful star far away may appear similar to a weaker star nearby. Spectra, motion, and geometry reveal the difference. The crew cannot navigate between stars by simply aiming toward the brightest point. Each object must be understood. Position changes over time. Stars move through the galaxy. The Sun moves too. The constellations are temporary arrangements. Over thousands of years, their familiar shapes change. Over millions, they become unrecognizable. There is no fixed ceiling. The sky is a moving population seen during one brief era. A detector records another change. Particles coming from the Sun have become less dominant. High-energy cosmic rays are increasing. These particles come from the galaxy beyond the heliosphere. Many are atomic nuclei traveling at tremendous energies. Some may have been accelerated by supernova remnants. Others may come from powerful environments that are still being studied. The heliosphere blocks or redirects part of this radiation. Beyond its stronger influence, the galactic environment becomes clearer. The spacecraft's shielding absorbs some particles. Others pass through. Radiation monitors continue counting. The crew has entered a region no human body has experienced before. Robotic spacecraft have crossed it. Human instruments have measured it. But no person has traveled this far from the Sun. The thought is significant. It does not change the procedure. Exposure is monitored. Time in protected areas is planned. Medical measurements are taken. The vehicle's shielding was designed for this environment. The unfamiliar becomes another set of numbers and routines. At last, the spacecraft approaches the heliopause. This is the broad boundary, where the solar wind's outward pressure is balanced by the pressure of interstellar material. Solar particles no longer dominate the surrounding plasma. The spacecraft is about to enter interstellar space. Again, there is no visible gate. The Sun still shines behind. Its gravity still reaches across the distance. Its light continues traveling outward. Crossing the heliopause does not mean leaving the solar system in every possible definition. Distant comets may still orbit the Sun much farther away. The star's gravitational influence extends deeply into space, but the local particle environment changes. The spacecraft moves from plasma shaped mainly by the Sun into plasma belonging to the region between stars. A magnetic field instrument reports a subtle shift. Particle detectors show a stronger change. Solar particles decrease. Galactic particles increase. Plasma density rises unexpectedly. The evidence accumulates. The crossing has occurred. The spacecraft is now traveling through interstellar space. Nothing outside looks different. This quiet absence of spectacle gives the moment its meaning. One of the greatest borders humanity can imagine has been crossed without a flash of light. No line passes beneath the hull. No voice announces arrival. The stars do not move. Only data reveals that the Sun's surrounding bubble now lies behind. The astronaut looks backward. The Sun appears as the brightest star in the sky. It is smaller than it once was, yet still easy to identify. Around that point travels every planet. Earth cannot be separated by the unaided eye. Jupiter is lost in the glare. Saturn's rings cannot be seen. The entire planetary system has contracted into one direction. The crew has not escaped the Sun's gravity, but visually, home and star have nearly merged. This is how distant planetary systems appear from Earth. A star shines, worlds orbit unseen. Their presence may be inferred because they pull slightly on the star, or because they pass in front and dim its light, or because their atmospheres leave faint chemical patterns. The astronaut now sees the Sun as another distant system might see it, a bright point carrying hidden planets. Perhaps an observer near another star would detect Jupiter first because of its size. Perhaps Earth would produce a tiny change in the Sun's light. Perhaps oxygen, water vapor, methane, or other atmospheric gases could suggest a living world. But no city would be visible, no individual signal would be obvious. Humanity's entire presence would be difficult to detect. Radio broadcasts weaken as they spread. Most are not aimed at distant stars. Atmospheric signs would be easier to observe than human activity. From far away, Earth might appear alive long before it appeared technological. This thought softens the idea of being watched. The galaxy contains enormous distance. Even a civilization with advanced instruments would need time, alignment, and attention to study Earth. It would see the planets past because light requires years to travel. A world 100 light-years away sees Earth as it was 100 years earlier. No observer sees the current moment from a great distance. The universe is filled with delayed images. Every telescope looks backward in time. The deeper the observation, the older the light. The astronaut faces the stars. Some light entering the window began traveling before human civilization. Some began before modern humans existed. Light from distant galaxies may have crossed space for billions of years. It reaches the glass. A small portion enters the eye. Ancient events become present perception. The universe does not reveal itself in real time. It offers messages carried by light. The spacecraft is now sending such messages too. Radio transmissions spread outward. They carry data about the crew, measurements, images, words. Most will never meet a receiver. They will continue weakening as they expand. But for a while, a small human pattern travels through interstellar space. The astronaut records an observation. The local particle environment is stable. The magnetic field remains within expected ranges. The Sun is visible behind. The spacecraft systems are normal. The statement sounds ordinary, yet no human has spoken it from this location before. Routine language has reached an unprecedented place. That is often how exploration advances. Not through constant drama, through ordinary sentences spoken where no one has spoken them before. The crew adjusts the antenna toward Earth. The beam must be narrow. A small pointing error across this distance could miss the receiving antennas by millions of kilometers. The spacecraft uses stars for orientation. Gyroscopes provide stability. Tiny thrusters or reaction wheels make corrections. The signal leaves. Hours pass before Earth can receive it. The crew will not know immediately whether it arrived clearly. They trust the calculations. Deep space has become a place where trust extends across time. Trust in navigation, in equipment, in colleagues, in people waiting far behind. The astronaut rests beside the window. Outside lies the interstellar medium. It is not completely empty. Atoms are present. Dust grains drift. Magnetic fields stretch through the galaxy. Cosmic rays pass. The density is still extraordinarily low. A container the size of a room may hold only a small number of particles compared with air on Earth. The region between stars is more vacant than any vacuum humans can create easily. Yet over light years, even sparse matter becomes important. Gas gathers into clouds. Gravity compresses some clouds. New stars form. Around those stars, disks may produce new planets. Emptiness is not a final state. It can be the space in which future worlds begin. The astronaut closes the eyes. The Sun's outer shelter is behind. The planets have disappeared into its distant light. The nearest star remains years away, even for a beam of light. The spacecraft floats between systems, protected by walls made on a small blue world no longer visible. The deeper journey has removed almost every familiar landmark, but it has not removed order. Particles still follow fields. Stars still move through gravity. Signals still cross distance. Matter still gathers. New suns still form. Beyond the Sun's last shelter, the universe is colder and wider. Yet it is not without structure. And within that interstellar quiet, one small human vessel continues forward, carrying warmth, memory, and a carefully aimed message back toward home. The spacecraft continues beyond the Sun. Behind it, the solar system has become a bright point. The planets can no longer be seen. The rings of Saturn have vanished. Jupiter's storms have disappeared. Earth, with all its oceans and cities, is hidden beside the distant star that once filled every morning sky. Ahead, there is no nearby destination. The next star remains unimaginably far away. Even after crossing the heliopause, the spacecraft has only taken its first step into interstellar space. The distance between stars is greater than the entire planetary journey that came before. A beam of light needs several years to reach the nearest neighboring system. The spacecraft travels far more slowly than light. At its present speed, the journey would extend across many human lifetimes. The crew will not reach another star. This mission was never designed to do so. Its purpose is to travel farther than any humans before it, studying the material between stars and observing the solar system from the outside. Still, the nearest stars remain ahead. Their light enters the windows. Their distance remains hidden. The sky looks crowded. Space remains almost completely empty. This contrast continues to shape every observation. A bright point may seem near. It may be dozens or hundreds of light years away. A faint cloud may appear small. It may be larger than the solar system. The human eye was shaped to understand nearby landscapes. A tree has a familiar size. A road narrows with distance. Mountains become hazy near the horizon. Interstellar space provides none of these clues. There is no horizon. No atmosphere creates haze. No familiar object offers scale. The mind sees a flat field of stars. Science turns that flatness into depth. Astronomers measure tiny shifts in stellar position as Earth moves around the Sun. This method is called parallax. Nearby stars appear to move slightly against more distant ones. The angle is extremely small, but it reveals distance. Other methods use brightness, color, pulsation, or exploding stars. Each technique extends the cosmic distance ladder farther outward. Through measurement, the sky becomes three-dimensional. One star is nearby, another lies behind it. A glowing cloud surrounds a newborn cluster. A galaxy exists far beyond them all. The spacecraft's instruments perform their own measurements. They observe cosmic rays. They sample interstellar particles. They study magnetic fields. They look backward toward the Sun and forward toward nearby stars. The crew records the changing environment. The work is slow. Interstellar space offers few sudden events. A detector counts particles over hours. A telescope gathers light over long exposures. The spacecraft rotates carefully. An antenna points toward Earth. Every action is deliberate, because every resource matters. Power is limited. Fuel is limited. Time is abundant. The crew's lives remain organized by artificial days. Lights brighten in the morning. They dim before rest. Meals divide work periods. Exercise protects muscles and bones. Medical measurements continue. The body needs rhythm, even when the universe provides none. There is no sunrise outside. The sun has become a star. It never rises or sets. The spacecraft creates morning through lighting. It creates evening through routine. Human time continues inside a place where the surrounding sky barely changes. This may be one of the deepest forms of distance. Not only distance from Earth, distance from the natural cycles that shaped human life. For millions of years, ancestors woke beneath changing light. They followed seasons. They watched shadows move. They slept when darkness arrived. Inside an interstellar vehicle, those patterns must be recreated. The crew lives by clocks built on Earth. A day remains 24 hours because the human body remembers the planet. The spacecraft carries Earth not only in its air and water, it carries Earth in time. Weeks pass. The sun becomes fainter. It remains the brightest star behind the vehicle, but the difference is shrinking. The next stars do not grow noticeably larger. The spacecraft is moving, yet interstellar distance changes the view with extraordinary slowness. A traveler crossing an ocean sees the coast vanish within hours. An interstellar traveler may spend years without seeing a destination grow. Motion becomes almost entirely mathematical. The navigation system confirms progress. The body sees stillness. The astronaut looks through the window. A faint glow stretches across part of the sky. It is the Milky Way. From Earth, this glow appears as a pale band under dark skies. Ancient observers saw a river, a path, a trail, or spilled milk. Its meaning varied across cultures. Its physical cause is now understood. The solar system lies inside a galaxy containing hundreds of billions of stars. From within its disk, The combined light of distant stars forms the broad band overhead. Dust blocks some regions. Bright star clouds fill others. The Milky Way is not a stripe wrapped around the universe. It is the galaxy seen from inside itself. The sun lies far from the center, within a smaller spiral feature called the Orion Spur. The galactic center is tens of thousands of light-years away. A massive black hole occupies its central region. Around it move dense populations of stars, gas, and dust. The spacecraft is not traveling toward that center. Even if it were, the journey would take far longer than human history. The galaxy is too large to cross using present propulsion. Light itself needs around 100,000 years to travel from one side of the Milky Way to the other. A human signal sent today will not reach the far edge within any familiar future. This scale changes the idea of searching for life. A civilization may exist on a distant world. Its signals may not have reached Earth yet. A signal arriving now may have been sent before human beings built cities. The civilization that transmitted it may have changed. It may have moved. It may no longer exist. Every interstellar message is also historical evidence. Communication across the galaxy is communication with the past. The astronaut thinks about radio waves leaving Earth. For more than a century, human technology has produced signals that travel outward. Some broadcasts have escaped into space. Radar transmissions may be stronger in particular directions. Deliberate messages have also been sent, but the expanding region reached by these signals is still small compared with the galaxy. Human radio has crossed only a tiny bubble around the Sun. Most of the Milky Way has never received evidence of modern Earth. Even within that bubble, signals become weaker with distance. A receiving civilization would need sensitive instruments and knowledge of where to look. The galaxy may contain life without producing easy conversation. Distance creates silence, even when minds exist on both sides. This silence does not prove emptiness. It reveals scale. The spacecraft detects a small increase in dust. The particles remain extremely sparse. The change is visible only through instruments. Some grains may have formed around old stars. Others may have passed through supernova explosions. They contain elements created inside stellar interiors: carbon, oxygen, silicon, iron. The atoms within the spacecraft's walls were also produced through ancient stellar processes. Hydrogen formed soon after the beginning of the universe. Heavier elements were built later inside stars or during violent cosmic events. The crew is not separate from the material outside. The difference lies in arrangement. Inside the spacecraft, atoms form metal, water, air, skin, memory, and thought. Outside, similar atoms drift alone across darkness. A small amount of matter has become organized enough to observe the rest. This is one of the quiet wonders of the journey. The universe is looking at itself through human eyes. The astronaut places a hand near the window. The glass reflects the fingers faintly. Beyond them, stars shine. The calcium inside the bones formed through earlier generations of stars. The iron in the blood came from cosmic events that occurred before the sun existed. Every breath contains material older than Earth. Deep space feels foreign, yet its matter is familiar. Human bodies are made from the same periodic table. The universe did not create life from special substance hidden elsewhere. It used common elements under uncommon conditions. Carbon formed complex bonds. Water remained liquid. Energy flowed. Chemistry became biology. Biology became awareness. Awareness built a spacecraft. The deeper the journey continues, the less meaningful it becomes to describe humanity as separate from space. Earth is not outside the universe. It is one expression of it. The spacecraft receives a message from home. The signal has traveled for many hours. Its strength is weak. The antenna collects it carefully. The recording begins with mission information, system updates, scientific instructions, a revised schedule, then personal messages follow. A child speaks about school. Someone describes rain. A family member mentions birds gathering near a window. These details feel more distant than any planet. Rain has not touched the crew for years. Birdsong cannot exist outside the spacecraft. Soil, wind, trees, and open water have become memories. The astronaut listens twice. The message contains no major news. That makes it more valuable. Ordinary life continues. Earth has not become a frozen image left behind. It remains active. Clouds move. People wake and sleep. New conversations begin. Meals are prepared. Doors open. The planet continues carrying billions of separate lives around the sun. The crew records a reply. The astronaut describes the Milky Way, the particle readings, the faintness of the sun. Then the astronaut describes the cabin. A filter was replaced. Breadcrumbs escaped from a package. Someone laughed while trying to catch them. Ordinary life continues here too. The message leaves the spacecraft. It travels backward at the speed of light. The crew cannot follow it. There is no immediate proof that it will arrive. The antenna remains pointed toward Earth for the required time. Then the spacecraft turns toward a scientific target. Trust returns. Somewhere behind, a planet listens. The journey continues. The spacecraft passes no planets. No moons cross the window. No unknown vessel appears. The greatest challenge is not an encounter. It is duration. Machines age. Radiation slowly affects materials. Seals must remain reliable. Electronic components accumulate damage. Human bodies change. Isolation changes attention and emotion. A mission measured in years requires more than strong hardware. It requires a stable community. Small disagreements must be managed. Privacy must be respected. Responsibilities must be shared. A crew cannot escape one another. Every voice belongs to the same small world. Psychological health becomes part of life support. Sleep matters. Conversation matters. Meaningful work matters. Humor matters. A window matters. Plants may matter too. A small growing chamber produces herbs and leafy vegetables. The plants contribute little to the total food supply. Their value extends beyond calories. Green leaves change the cabin's appearance. The smell of living soil or growing material, when safely contained, creates a connection to Earth. New growth marks time. A seed opens, roots form, leaves unfold. The process is slow enough to watch across days. Outside the spacecraft, stars change almost imperceptibly. Inside, a plant grows toward artificial light. Life creates visible time. The astronaut cares for the plants during each work period. Water must be delivered carefully in microgravity. Roots need moisture and oxygen. Airflow prevents excessive humidity around leaves. Light follows a controlled schedule. The plants depend on machinery, just as the crew does. Yet they respond biologically. They bend, expand, change color. A new leaf appears. The crew harvests a small portion for a meal. The taste is simple. Freshness has become rare. The leaves carry the smell of something recently alive. For a few minutes, the spacecraft feels less mechanical. The deeper the mission travels, the more valuable life becomes. Not because life has changed, because the surrounding environment offers so little of it. A single green plant can be more visually striking than an entire field was on Earth. A drop of liquid water becomes something watched carefully. A human voice becomes an event after hours of silence. Scarcity sharpens attention. This may be why the journey can seem more unsettling with distance. The universe does not become more hostile in intention. It becomes less similar to the conditions humans need. Near Earth, air, water, gravity, sunlight, and help exist close together. Between stars, every one of these must be carried or created. The farther the spacecraft moves, the more complete its responsibility becomes. There is no natural refuge nearby. No planet can be reached quickly. No rescue vehicle can cross the distance. The spacecraft must continue being a world. During one quiet period, the navigation system detects an unexpected change in attitude. The shift is extremely small. A reaction wheel has begun producing more vibration than expected. The wheel helps rotate the spacecraft without using fuel. Internal momentum changes the vehicle's orientation. The system has operated for years. Now a bearing may be wearing. The crew studies the data. The wheel still functions, but vibration is increasing. A backup system is available. The spacecraft can also use small thrusters. The crew decides to reduce load on the affected wheel. Responsibility is transferred gradually. The wheel slows. Another unit takes over. The vibration decreases. There is no dramatic failure. A machine has simply aged. Its condition becomes part of the mission's future planning. Engineers on Earth will receive the data later. They may suggest additional tests. For now, the crew acts. This small event carries the meaning of the journey. The problem is manageable, but every replacement used reduces future options. Deep space turns reliability into a resource. A machine does not need to fail suddenly to matter. A slow change can shape decisions years later. The crew records every detail: sound, temperature, power use, vibration, time. The component becomes a story told through measurements. The spacecraft continues. Far ahead, a dark object moves through interstellar space. It is not visible yet. Astronomers discovered it through the way it briefly bent and magnified the light of a background star. The object may be a rogue planet. Such worlds do not orbit a star. They travel alone through the galaxy. Some may have formed directly from collapsing gas. Others may have been ejected from planetary systems through gravitational interactions. A planet can lose its star. It can move through darkness for billions of years. The spacecraft will not pass close to this object. Its predicted path remains far away. But the discovery changes the crew's image of interstellar space. Not every world gathers around sunlight. Some planets wander between stars. Their surfaces may be frozen, yet internal heat can remain. A thick atmosphere might trap warmth. A subsurface ocean could survive beneath ice. A moon could continue orbiting. The absence of sunlight does not guarantee complete inactivity. The galaxy may contain more hidden worlds than visible ones. The astronaut looks into the darkness. Nothing can be seen where the rogue planet moves. It reflects almost no light. Only gravity revealed it. A world can be present without appearing. This fact feels mysterious, but not supernatural. Mass bends space and influences light. Astronomers observe the effect. The invisible object becomes measurable. Once again, science does not remove wonder. It gives wonder a structure. The journey continues past no marked boundary. The spacecraft remains inside the Milky Way. To leave the galaxy would require crossing distances far greater than those already traveled. Beyond the Milky Way lie smaller satellite galaxies. Farther away is Andromeda. Its light has traveled more than 2 million years to reach the spacecraft. The image seen now began before modern humans existed. Andromeda appears as a faint patch. Through instruments, it becomes a spiral galaxy filled with stars, gas, dust, black holes, planets, and perhaps life. The Milky Way and Andromeda are moving toward one another. In several billion years, their structures will interact and eventually merge. Individual stars are so widely separated that most will not collide. But gravity will reshape both galaxies. New orbits will form. Gas clouds may compress. Star formation may increase. The night sky of distant future worlds will look completely different. Galaxies are not fixed islands. They grow, merge, distort, separate matter into new patterns. Beyond the local group of galaxies lie clusters and superclusters. They form long filaments around immense cosmic voids. On the largest scales, matter resembles a web. Galaxies gather along its strands. Vast regions between them contain very little. The darkness between stars once seemed empty. The darkness between galaxies is emptier still. A spacecraft placed in a great cosmic void might see fewer bright galaxies. The nearest large structures could be millions of light years away. No human mission can travel there. The crew experiences this idea only through observation and mathematics. Yet the scale affects the imagination. The universe contains regions where whole galaxies are the distant landmarks. The deeper one looks, the less central any one world appears. Earth becomes one planet. The Sun becomes one star. The Milky Way becomes one galaxy. The local group becomes one small gathering among many. Every widening view removes another imagined center. This can feel unsettling. Human beings prefer orientation. A room has walls. A city has streets. A map has edges. The observable universe has a horizon, but not a wall. The horizon exists because light has had a limited time to reach the observer. Beyond it may lie more universe. Its light has not reached this location. The boundary belongs to observation, not necessarily to space itself. Every observer has a different cosmic horizon. There may be regions so distant that no signal sent now will ever reach Earth because the expansion of the universe carries them away too quickly. Their light may fade from future view. Some galaxies visible today will eventually become unreachable, even in principle. The universe contains separation deeper than ordinary distance. There are places that time and expansion may permanently remove from contact. The astronaut sits quietly with this thought. No danger approaches the spacecraft. The cabin remains secure. The idea itself is large. Some parts of reality may never be known directly. Science can describe limits. it cannot always remove them. There will be light humanity never receives, worlds humanity never sees, questions no mission can answer. The deeper journey becomes less frightening when uncertainty is not treated as failure. Not knowing is a natural part of observing a universe larger than any observer. Knowledge grows within boundaries. Every measurement reduces some uncertainty while revealing more beyond it. A telescope discovers a galaxy. The galaxy contains billions of stars. A planet is detected. Its atmosphere raises new questions. A signal is found. Its source must be understood. Discovery does not end mystery, it refines it. The astronaut returns to the window. The sun remains behind. A small plant grows nearby. Human voices rest inside stored messages. The spacecraft moves through interstellar gas. The Milky Way surrounds it. Galaxies shine beyond. The universe feels more severe than it did near Earth, because shelter has become rare, distance immense, and time unavoidable. But it also feels calmer. Nothing outside is rushing. Stars live for millions or billions of years. Galaxies turn slowly. Light crosses darkness without tiring. The spacecraft's journey is brief beside these processes. Even a human lifetime is a moment. This does not make the crew unimportant. It makes their awareness remarkable. For a short time, matter has become able to notice scale, to measure darkness, to ask where it came from, to send a message home. The astronaut records the final observation of the day. The spacecraft remains stable. The replacement reaction wheel is operating normally. Particle counts are within expected ranges. The plant chamber has produced a new leaf. The distant sun remains visible. The report is simple. It contains both machine and life. The crew dims the cabin lights. One by one, voices become quiet. Air continues circulating. The spacecraft keeps its antenna oriented toward Earth. A faint signal arrives from behind. It carries recorded ocean waves. Someone on Earth included them for the crew. Water rises and falls against a shore. Wind moves above it. The sound fills the cabin softly. No ocean lies nearby. Yet the pattern of one has crossed interstellar space. The astronaut closes the eyes. For a moment, distance becomes sound. Earth is not visible, but it is present. Present in the body's rhythm, in recycled water, in the names of stars, in the language used to describe them, in the memory of gravity, in the recorded movement of waves. The deeper one travels into space, the more unfamiliar the universe becomes. Protection grows thinner. Answers take longer. The darkness expands. But the deeper one travels, the more clearly home can also be understood. It is not only a location, it is a collection of conditions. Warmth, air, water, life, memory, connection. These can be carried, shared, recreated, protected. Outside, the universe continues without sound. No hidden watcher moves among the stars. No presence follows the spacecraft. There is only matter, energy, time, gravity, and distance. These are powerful enough. They shape planets, ignite stars, build galaxies, separate worlds, and sometimes, under rare conditions, they create beings capable of feeling wonder at them. The astronaut drifts into sleep. The spacecraft continues forward. The sun shines behind as a distant point. The nearest stars remain far ahead. The ocean recording fades. Only the quiet mechanical breathing of the cabin remains. Humanity has gone deeper than ever before. The universe has become colder, wider, and less forgiving. Yet inside one small moving world, light remains warm, air remains steady, a new leaf continues opening, and across the long darkness behind them, Earth is still listening. Good night.